Hello there, and welcome to Science for Sleep, a place where curiosity is invited to slow down, stretch out, and get comfortable, where questions about the universe are not meant to be solved quickly, but gently explored, like turning over a smooth stone in your hand while the day finally lets go of you. Wherever you are right now, whatever kind of day you've had, this is a moment to pause. You don't need to concentrate too hard. You don't need to remember everything that's said. You can simply listen. Let the words pass through at their own pace, and allow your thoughts to soften as we wander together through an idea that is strange, familiar, and quietly confusing all at once. Tonight, we're going to be talking about distance. Not the kind you measure on a road trip or feel when someone you care about lives far away, but a distance so oddly defined that even people who work with it every day sometimes have to stop and think twice. A distance with a name that sounds like it should belong to time or speed, or maybe a setting on a piece of scientific equipment, rather than something you'd use to describe how far apart two things are. That distance is called a parsec, and the more you look at it, the more it seems to resist common sense in a very calm, unapologetic way. Before we ease into that, take a moment to notice where you are. Are you listening in bed, with the lights already dimmed or maybe still on, casting that soft glow that makes the room feel smaller and quieter? Are you stretched out on a sofa, or resting somewhere in between sleep and wakefulness, where thoughts begin to drift without asking permission? What part of the world are you in right now, and what time is it there, in your particular corner of the spinning planet? It's a fitting question, because even as we talk about distances that stretch far beyond imagination, all of this is happening in a very small, very specific moment for you. If you find this space soothing, or if you enjoy these slow, careful walks through science that don't demand anything from you, then you might consider liking the video or subscribing. It helps this quiet little project reach other people who could use a calm place to land at the end of the day. There's no rush though. That can wait. For now, there's nothing you need to do except listen. When most of us think about distance, we think in familiar terms. Steps, meters, miles, kilometers. The length of a room, the span of a city, the stretch between one town and the next. Even larger distances like crossing an ocean or flying halfway around the world still fit comfortably inside ideas we've grown up with. They're big, certainly, but they behave the way distance is supposed to behave. Double the distance and it feels like twice as far. Cut it in half and it makes sense in your head. There's an intuition to it that rarely lets you down. Space, however, does not care about that intuition. Once you leave Earth behind, even just conceptually, the numbers start to misbehave. Distances grow so large so quickly that the units we're used to become awkward, then useless, then almost silly. Saying that a nearby star is tens of trillions of kilometers away is technically correct, but it doesn't really help your brain picture anything. It's like trying to understand the size of the ocean by counting individual drops of water. The numbers are real, but they stop being meaningful. So astronomers did what humans almost always do when faced with something too big, too strange, or too inconvenient. They invented a new way to talk about it. That's where the parsec comes in. Not as a dramatic invention, not as a flashy breakthrough, but as a practical solution to a very specific problem. And like many practical solutions in science, it ended up sounding far more confusing than the thing it was meant to replace. The word itself doesn't offer much help. Parsec sounds technical, clipped, almost mechanical. It doesn't hint at distance. It doesn't suggest size. If anything, it feels like it belongs on a control panel or inside a piece of machinery humming quietly in the background. It's no wonder that people often assume it has something to do with time. It even sounds a bit like second or pass or some hybrid of speed and duration. And yet, despite its reputation and its unfortunate name, a parsec is simply a way of describing how far away something is. Still, there's something deeply unintuitive about it. Unlike kilometers or miles, a parsec isn't defined by a fixed length you could, in theory, lay end to end. It's defined by geometry. by angles, by the way objects appear to shift against a background when your point of view changes. It's a distance that only makes sense if you imagine standing on Earth at one moment, then standing somewhere else at another, and carefully noticing how the sky rearranges itself just a tiny bit because of that movement. That alone should tell you that we're already far from everyday experience. Think about how rarely you need to measure distance using angles in normal life. You might glance at the way a nearby object shifts when you move your head, or notice how your finger seems to jump against the background when you hold it up and close one eye then the other. But you don't build your sense of the world around those shifts. You rely on size, perspective, and memory. You know how big a car is. You know roughly how tall a building should be. Distance behaves. In astronomy, distance does not behave. Stars don't come with labels telling you how large they are. They don't politely arrange themselves at different sizes so your brain can sort them out. Many stars that look bright are actually far away and enormous. Others that look faint may be much closer but smaller, or simply less energetic. Your eyes, helpful as they are on Earth, are easily misled when pointed at the sky. So instead of asking how bright something looks, or how large it appears, astronomers learn to ask a different question. How much does it shift? Not dramatically. Not in a way you'd notice without careful instruments. But enough to measure if you're patient and precise. Imagine standing in one spot and looking at a distant object like a mountain on the horizon. Now imagine walking several steps to the side and looking again. The mountain hasn't moved, but your position has, and because of that, its position relative to even more distant objects changes slightly. This effect is called parallax, and it's something your brain uses all the time without you noticing. It's how you judge depth. It's how you can tell that one thing is closer than another. In space, the baseline for this shift isn't a few steps. It's the width of Earth's orbit around the Sun. That's already an uncomfortable leap in scale, and we haven't even defined the parsec yet. As Earth moves around the Sun, our viewpoint changes. In January, we're on one side of the orbit. 6 months later, we're on the opposite side. From those two positions, nearby stars appear to shift slightly against the background of much more distant stars. The closer a star is, the larger that tiny shift appears. The farther away it is, the smaller the shift becomes, until it eventually disappears into the limits of measurement. A parsec is defined using that shift. Specifically, it's the distance at which a star would show a parallax angle of 1 arcsecond when observed from opposite sides of Earth's orbit. An arcsecond, by the way, is not a second, it's an angle. 1/3600th of a degree. Already, the definition is politely asking your intuition to sit down and be quiet for a while. And yet, for astronomers, this definition is beautifully clean. It ties distance directly to observation. It doesn't require knowing how bright a star truly is. It doesn't depend on assumptions about size or composition. It relies only on geometry and careful measurement. If you can measure the angle, you can calculate the distance. That's the elegance hiding inside the confusion. Still, from a human perspective, it feels backward. We're used to defining distance first, then measuring angles if we need to. The parsec flips that relationship around. It says, measure the angle, and the distance will reveal itself. It's not a ruler, it's a consequence. This is why parsecs tend to feel slippery when you first encounter them. They don't map cleanly onto daily experience. You can't picture a parsec the way you can picture a kilometre. You can't walk it, drive it, or fly it. Even light, racing along at its absurd speed, takes more than 3 years to cross a single parsec, and that fact alone often leads people to quietly retreat back to light years, which at least sound like they're being honest about what they are. But the parsec persists, not because it's friendly, but because it's useful. It's the unit that naturally falls out of the way astronomers actually measure the sky. It's not an arbitrary choice, it's baked into the method. And once you accept that, once you stop trying to force it to behave like a terrestrial distance, it begins to feel less like nonsense and more like a reminder that space operates on its own terms. For now, It's enough to recognize that the parsec exists because the universe is large in a way that refuses to fit neatly into human habits. And that, in its own quiet way, is part of what makes learning about it so strangely calming. At first glance, the word itself already seems to be working against you. Parsec. It doesn't sound like distance. It doesn't stretch out the way kilometre does, or roll along the way mile does. It snaps shut almost as soon as it's spoken, a compact little term that gives no hint of scale, direction, or feeling. If someone were to mention it casually in conversation, without context, you might reasonably assume it refers to a process, a device, or maybe a setting buried somewhere deep in a technical manual. Very few people would hear the word and think, ah yes, that must describe a staggeringly large span of space between stars. That unease is not accidental. It's a signal that something about this unit does not align with the way humans usually relate words to experience. Most units of distance earn their names through familiarity or physical reference. A foot was once a foot. A meter was tied to the Earth itself. Even when definitions evolve and become more precise, the words remain anchored in something you can imagine. A kilometre suggests length. A mile suggests travel. They imply movement, effort, duration. You might not know exactly how long they are without thinking, but your body has a relationship with them. A parsec offers none of that. It doesn't suggest walking, driving, or even flying. It doesn't hint at time passing or effort expended. It simply exists as a label detached from instinct, hovering somewhere between mathematics and astronomy. That detachment is often the first thing that makes people uncomfortable with it. We are used to units that cooperate with our intuition. The parsec refuses. Part of the problem lies in how the word is constructed. Parsec is not a poetic invention or a descriptive phrase. It's a contraction, a compressed technical shorthand that comes from parallax of 1 arcsecond. That origin explains its usefulness, but it also explains why it feels so alien. It was never meant to sound friendly. It was meant to be efficient. Efficiency, however, is rarely comforting. When you hear light year, even if you don't know exactly how far it is, the name does some of the work for you. Light suggests speed. Year suggests time. You instinctively understand that this distance is tied to how far something extremely fast can go over a long duration. The scale is still enormous, but the concept meets you halfway. Parsec does not meet you halfway. It stands its ground and waits. This is why parsecs are often described as confusing, misleading, or counterintuitive, especially outside professional astronomy. The name does not tell you what you want to know. It doesn't answer the question your brain asks first, which is usually, how far is that, really? Instead, it quietly insists that you ask a different question altogether. And that difference is the key. Humans evolved to judge distance locally. How far to the next tree? How far to shelter? How far before nightfall? Our brains are excellent at estimating distance within a landscape, especially when we can move through it. The sky, on the other hand, offers no such feedback. You cannot approach a star and watch it grow larger. You cannot feel the distance to a galaxy in your legs or lungs. Everything above you is flattened onto this same dome, equally unreachable. Early attempts to understand cosmic distance struggled precisely because of this. For centuries, astronomers could track the motion of planets, predict eclipses, and map the sky with impressive precision, yet the stars themselves remained stubbornly dimensionless. They were points of light, each seemingly pinned to the same surface, regardless of how bright or faint they appeared. Brightness, it turns out, is a terrible guide. A nearby dim star and a distant luminous star can look nearly identical from Earth. Without knowing how much light a star truly emits, brightness alone tells you very little about how far away it is. Size is no help either. Stars are too distant for their disks to be resolved with the naked eye, and for most of human history, even telescopes offered little clarity. So astronomers needed a method that did not rely on assumptions about what stars are like. They needed something geometric, something that depended only on position and movement, something that could be measured without knowing anything about the object itself. This is where the parsec quietly begins to make sense, even if its name still feels uncooperative. The parsec does not describe distance as an absolute stretch through space. It describes distance as a relationship between observation points. It asks you to care less about how far something is in kilometers and more about how it behaves when you change your perspective. That's a deeply non-human way of thinking about distance. We usually treat distance as fixed. An object is either 10 meters away or it isn't. But the parsec is defined by how much a star appears to shift when the observer moves. That shift, known as parallax, is tiny, subtle, and entirely dependent on geometry. The unit is born not from the star itself, but from the dance between Earth's motion and the background of the universe. So when someone says a star is 1 parsec away, what they're really saying is this: if you observe that star from one side of Earth's orbit, then observe it again 6 months later from the opposite side, the star's apparent position against distant background stars shifts by exactly 1 arc second. That is the entire definition. No kilometers required. If that feels unsatisfying, that's because it is. At least at first. An arc second is an absurdly small angle. To give it some grounding, imagine dividing a single degree into 3,600 equal parts. One of those parts is an arc second. Now imagine trying to notice such a shift in a point of light that is trillions of kilometers away. This is not a measurement your senses evolved to handle. It requires precision instruments, careful calibration, and a great deal of patience. And yet, this awkwardness is precisely why the parsec exists. It aligns perfectly with the difficulty of the task. Instead of fighting the limitations of observation, astronomers leaned into them. They defined distance in terms of the smallest measurable angular shift that could reliably be detected. The parsec is not a natural unit in the human sense. It is a natural unit in the observational sense. Still, the name remains a problem. Because it doesn't tell you what it's doing, the parsec is often misunderstood. People assume it's arbitrary. They assume it's just another way of saying light year, perhaps with a different scaling factor. Or worse, they assume it's time measurement. The fact that this confusion is so common is not a failure of education. It's a mismatch between language and expectation. Words carry weight. They shape how concepts settle in the mind. When a word refuses to cooperate, the concept it represents tends to remain slippery. There is also the cultural layer to consider. Outside of textbooks and observatories, parsecs are most often encountered in fiction, and fiction has not always been kind to them. They are sometimes misused, conflated with speed, or thrown into dialogue as a marker of scientific credibility rather than accuracy. Each time this happens, the parsec drifts a little further from its original meaning in the public imagination. This doesn't help its reputation, but reputation aside, the parsec continues to do its job quietly and reliably. Astronomers use it because it integrates seamlessly into their measurements. Distances to nearby stars are measured in parsecs. Larger structures are described in kiloparsecs. Entire galaxies are mapped in megaparsecs. The unit scales naturally with the universe it describes, even if it never feels natural to us. And perhaps that discomfort is worth paying attention to. The parsec feels wrong because it exposes a gap between human intuition and cosmic reality. It reminds us that the universe was not built to be easily understood from the surface of one small planet. Our everyday units fail not because they are flawed, but because they are local. The parsec is a tool designed for a different arena, one where Earth itself becomes part of the measuring apparatus. When you think about it that way, the name begins to feel less like a mistake and more like an honest admission. This is not distance as you know it. This is distance as the universe allows it to be measured. There is also something quietly humbling about the fact that the parsec depends on Earth's motion. Without our planet's orbit, without that steady journey around the sun, the definition collapses. The parsec is anchored not in space alone, but in movement. It exists because we are not standing still. That idea tends to slip past unnoticed, but it matters. Distance, in this sense, is not an isolated property. It emerges from relationships, from angles, from perspective, from motion. The parsec encodes all of that into a single, stubbornly opaque word. So yes, the name feels wrong. It feels technical, clipped, unhelpful. But it also carries within it a very specific story about how humans learn to measure something they could never reach. It represents a compromise between what can be observed and what can be imagined. As we continue, it becomes useful to let go of the expectation that the parsec should behave like familiar distances. It isn't meant to. It was never designed for comfort or intuition. It was designed to solve a problem quietly and consistently, and in that sense it succeeds remarkably well. Once that shift happens, once you stop asking the parsec to make sense on human terms, it begins to settle into place, not as a friendly concept, but as a reliable one. There is a moment, often quiet and easily missed, when familiar numbers stop being helpful. It usually happens not all at once, but gradually, as quantities grow larger and larger, until the mind can no longer attach them to anything concrete. Space reaches that moment very quickly, faster than most people expect. One moment you're talking about thousands, then millions, then billions, and suddenly the numbers keep increasing while your sense of what they mean stays behind, blinking politely, unable to follow. On Earth, numbers cooperate, they behave. If someone tells you a distance is 10 kilometers, you might not picture every meter, but you have a sense of effort, of time, of motion. You know what 10 kilometers does to legs, fuel tanks, or train schedules. If the distance doubles, your expectations double with it. The relationship holds. Space breaks that relationship almost immediately. The first problem is scale. The universe does not scale gently. It does not ease you into larger distances in a way that allows intuition to adapt. It jumps. The distance to the moon already stretches everyday numbers. The distance to the sun makes them wobble. The distance to the nearest star snaps them clean in half and keeps going. Each step outward is not just bigger. It is so much bigger that the previous step becomes irrelevant. Take kilometers, for example. They work beautifully on Earth. They work reasonably well for describing orbits around the planet, but the moment you try to use them for interstellar distances, they become absurdly verbose. You end up stacking zeros until the number itself becomes the story. Saying that a nearby star is roughly 40 trillion kilometers away may be accurate, but accuracy alone does not guarantee usefulness. At some point, the number stops informing and starts overwhelming. This is where space quietly refuses to cooperate with familiar units. It is not being difficult on purpose. It simply operates on scales that those units were never designed to handle. Human measurement systems evolved to solve human problems. How far can you walk before nightfall? How much land needs to be measured for farming? How far apart are settlements? Even later refinements tied to planetary dimensions or physical constants were still anchored to a world where distances could, at least in theory, be traversed or imagined as continuous stretches. Interstellar space cannot be traversed in that way. There is no journey you can picture, no gradual passing of landmarks, no sense of accumulation. You are forced to accept distance as an abstract separation rather than an experienced one. Numbers struggle in that environment. There is also a second, quieter problem. Space does not offer reference points that help numbers feel grounded. On Earth, distance is often contextual. 10 kilometers across a city feels different than 10 kilometers across a desert, but the scale remains anchored to surroundings. In space, surroundings vanish. A star does not appear closer because it sits near another star in your field of view. Everything floats against a background that offers no depth cues your brain can trust. So when you attach a familiar number to an unfamiliar context, the number loses its anchoring function. It becomes symbolic rather than descriptive. This is why astronomers did not simply invent larger versions of existing units and call it a day. They could have defined a megakilometre or a terakilometre and continued counting. Technically, nothing stopped them. But those numbers would still fail to connect measurement to observation. They would describe size without describing how size is known. Space, as it turns out, is not impressed by numbers that cannot be observed. The distances we care about in astronomy are not distances we measure by stretching a ruler from one point to another. They are distances inferred from light, angles, motion, and timing. They emerge from relationships rather than direct measurement. A unit that ignores this fact is already at a disadvantage. This is where familiar numbers begin to feel not just large, but wrong. When astronomers observe the sky, they do not start by asking how many kilometers away a star is. That question cannot be answered directly. Instead, they ask questions like, how bright does it appear compared to similar stars? How does its spectrum shift? How does its position change relative to background objects as Earth moves? These questions produce ratios, angles, and relative changes, not absolute lengths. Trying to force those observations into familiar numbers adds an unnecessary translation step. It is like converting temperature into distance, or sound into weight. The information survives the conversion, but clarity does not. This is one of the reasons space ends up with its own numerical language. It is not a matter of preference or tradition. It is a matter of efficiency. Units like the Parsec arise because they align directly with how space reveals itself to us. Still, even before we get to specific units, there is a deeper resistance at work. Space refuses familiar numbers because familiar numbers imply familiarity. They suggest that the thing being measured behaves like things we already understand. Space does not. Consider how distance behaves within a gravitational field. Distances warp. Paths curve. Straight lines are no longer simple. Even the idea of simultaneity, which underpins how we often think about measuring separation, begins to unravel. When space itself can stretch and bend, attaching it to a static number becomes conceptually fragile. Familiar numbers assume a stable stage. Space is not a stable stage. Even in relatively calm cosmic neighborhoods, motion complicates everything. Stars move, galaxies drift. The expansion of the universe stretches the space between distant objects over time. A distance defined at one moment is not quite the same distance at another. This does not matter much on Earth. It matters enormously across billions of light years. So space refuses numbers that pretend time, motion, and perspective do not exist. There is also the issue of precision. Familiar units imply a level of certainty that space rarely provides. Saying something is exactly 10 meters away feels reasonable. Saying something is exactly 40 trillion kilometers away implies a degree of confidence that is often unwarranted. Astronomical distances are usually estimates, refined over time as measurements improve. They are surrounded by error bars, assumptions, and evolving models. Units like the Parsec are honest about this. They embed uncertainty into their use. A parallax angle can be measured more precisely or less precisely. The resulting distance inherits that uncertainty naturally. The number does not pretend to be exact. It reflects the limits of observation. This honesty is uncomfortable for everyday thinking, but it is essential for science. There is another subtle reason space resists familiar numbers. Our brains are not linear when it comes to large quantities. We handle differences well at small scales, but our perception compresses rapidly as values grow. The difference between 1 and 10 feels large. The difference between 1 billion and 10 billion does not feel 10 times larger, even though it is. Space lives entirely in that compressed region of perception. When you say a star is 1 light year away versus 10 light years away, the difference feels modest, even though it represents trillions of kilometers. When you say a galaxy is 10 million light years away instead of 1 million, the difference barely registers emotionally. Familiar numbers stop carrying proportional meaning. This is why astronomers often work in powers, prefixes, and categories rather than raw values. They speak in orders of magnitude, They group distances into regimes, nearby stars, local galactic neighbourhood, intergalactic space. Each category represents a qualitative shift rather than a quantitative one. Familiar numbers do not like this kind of categorization. They want smooth continuity. Space offers abrupt transitions. It is also worth noting that our attachment to familiar numbers is cultural as much as cognitive. We are taught to trust certain units. We grow up with them. They become part of how we describe effort, cost, and value. When space refuses those units, it feels like a rejection of shared language. But space is not obligated to speak our language. It existed long before we named distances. It will continue long after our units evolve or disappear. The fact that we must adapt our numerical systems to fit it is not a failure of understanding. It is evidence of humility. This adaptation does not happen only once. It happens repeatedly as we push further outward. First kilometers fail, then astronomical units become unwieldy. Then light years lose immediacy. Then even parsecs give way to larger constructions. Each step reflects not confusion, but refinement. We learn which numbers matter in which contexts. There is something quietly reassuring about this process. It suggests that science is not about forcing reality into comfortable frameworks, but about listening carefully enough to let reality suggest better ones. Space refuses familiar numbers because it requires different questions, not because it delights in being obscure. And once you accept that refusal, once you stop trying to make space behave like a landscape you could cross, a shift happens. Numbers stop being obstacles and start becoming guides. They point not to distance as a thing you travel, but to distance as a relationship you infer. For most of human history, distance was something you could feel in your body. It was measured in footsteps, in the ache of legs after a long walk, in the time it took the sun to move from one position in the sky to another. Even when those measures became more formal, when miles and kilometers replaced paces and days, the underlying relationship stayed the same. Distance was still tied to effort. To move farther meant more work, more time, more resources. The numbers meant something because they were rooted in experience. That grounding holds remarkably well on Earth. A mile is not just a number. It is a stretch of road. It is the difference between walking and driving. It is a unit that carries with it assumptions about speed, terrain, and time. Even if you have never walked a full mile deliberately, your body understands it indirectly. You know roughly how long it would take. You know how it would feel. This quiet partnership between numbers and experience is what makes earthly distances so cooperative. They fit into mental models that evolved to handle landscapes, not voids. The moment you look upward, that partnership begins to unravel. At first, the breakdown is subtle. The moon, after all, is far, but not unimaginably so. Its distance can be expressed in kilometers without immediately causing distress. The number is large, yes, but it still feels finite, approachable in theory if not in practice. You can imagine travelling there, even if the logistics are daunting. Then comes the sun. The distance between Earth and the sun already pushes familiar units toward their limits. Millions of kilometers stop behaving like normal numbers. They start to feel ceremonial, something recited rather than understood. Astronomers respond by inventing a new convenience, the astronomical unit, defined by Earth's orbit itself. This helps for a while. It restores some sense of scale, some connection to something real, but the relief is temporary. As soon as you leave the solar system, even the astronomical unit collapses under the weight of what it is asked to describe. Stars are not a few dozen or even a few hundred astronomical units away. They are hundreds of thousands of them away. Millions. The numbers swell, and once again the unit begins to creak. This is where stellar confusion sets in. Trying to describe interstellar distances using Earth-based units is like trying to describe the size of an ocean in teaspoons. The conversion is possible, but the result is useless. You end up with numbers so large that they stop informing and start numbing. They no longer communicate scale, they obscure it. There is also an emotional component to this confusion. earthly miles come with expectations, they suggest accessibility, or at least potential accessibility. Even a very long journey across Earth feels bounded. There is an end point that can be reached with enough time and planning. Stellar distances do not offer that comfort. They are not just longer, they are categorically different. This difference matters because our brains are not good at handling categories that break familiar rules. When you hear that a star is trillions of miles away, your mind tries to map that statement onto what it already knows. It imagines a very long road or an extremely long flight. But those metaphors fail almost immediately. There is no road, there is no refueling stop, there is no gradual approach. The distance does not unfold, it simply exists. And so the number becomes abstract in a way earthly numbers never quite are. This abstraction is amplified by the fact that space offers no intermediate feedback. On Earth, you always have a sense of progress. You pass landmarks, you cross borders, you feel the distance diminishing. In space, especially when talking about stars, there is no such gradient. The star looks the same from almost anywhere within the solar system. Its distance does not announce itself visually in a way your brain can parse. So when you attach earthly units to stellar separation, the units lose their meaning faster than expected. Astronomers recognized this early on, even before they could measure stellar distances accurately. There was a long period in which the distances to stars were simply unknown, not because of a lack of curiosity, but because existing tools and concepts were insufficient. People could measure angles, track motions, predict celestial events, but the depth of the universe remained stubbornly flat. The failure was not observational alone, it was conceptual. Earth-based distance assumes that the observer is separate from the measuring apparatus. You lay down a ruler, you count steps, you send a signal and measure the return. In space, especially at stellar scales, the observer is part of the system. Earth's motion becomes the baseline. Time becomes part of the measurement. Angles matter more than lengths. This is not how miles are meant to work. Miles assume a static frame. They assume that space itself is neutral, a backdrop against which objects sit quietly waiting to be measured. Space refuses this role. It moves, it curves, it expands, it drags time along with it. A mile in one context is not equivalent to a mile in another, once you leave the comfortable regime of low speeds and weak gravity. So the confusion is not just about large numbers, it is about broken assumptions. Earthly miles imply that distance is something you can imagine accumulating. Stellar distances demand that you abandon that image. They are not accumulated, they are inferred. They are conclusions drawn from subtle effects that only become meaningful when viewed statistically and geometrically. This is deeply unsatisfying to intuition. It feels backwards. You want to know how far something is, not how it shifts when you move. You want a number that describes separation directly, not indirectly. But space does not offer direct access at those scales. It forces you to work with what can be observed. The result is a kind of conceptual vertigo. You know the numbers are real, you know the calculations are sound, but the connection between the number and any lived sense of distance is gone. This is why people often describe stellar distances as meaningless or incomprehensible. Not because they are poorly defined, but because they are defined in a way that bypasses human experience entirely. Even light years, often praised for their intuitive appeal, eventually succumb to this problem. A light year at least tells you something about time and speed. It suggests motion, but after a few dozen of them, that intuition collapses as well. The difference between 10 light years and 100 light years feels modest, even though it represents an enormous gulf. This flattening of perception is what turns confusion into something more persistent. Once numbers stop scaling emotionally, they stop serving their original purpose. They no longer help you compare, evaluate, or imagine. They become labels rather than measures. This is the point at which astronomers stop asking numbers to do emotional work and start asking them to do technical work instead. And that is where units like the parsec begin to feel necessary rather than strange. The parsec does not attempt to preserve the illusion that distance can be felt. It gives up on that project entirely. Instead, it encodes the method by which distance is determined. It says, this is not about how far you could go, but about how geometry behaves when you change perspective. In doing so, it acknowledges the failure of earthly miles outright. This is not a flaw, it is an adaptation. Stellar confusion arises when we try to force space into frameworks that evolved for survival on a planet. The confusion fades, or at least becomes manageable, when we allow space to dictate its own terms. That does not mean space becomes intuitive, it means our expectations adjust. You stop asking how long it would take to get somewhere, because that question has no useful answer. You stop imagining travel and start imagining relationships, angles, shifts, patterns, distributions. Distance becomes something you calculate, not something you traverse. There is a quiet relief in this shift, once it settles in. You're no longer obligated to understand stellar distances the way you understand earthly ones. You are allowed to let them be abstract without feeling that you have failed to grasp them properly. This does not make the universe smaller or more approachable. If anything, it emphasizes how far removed it is from human scale. But it also clarifies why familiar numbers fall apart so quickly once you leave Earth behind. They were never meant to survive that journey. As this understanding deepens, the transition from miles to parsecs begins to feel less like a betrayal of intuition and more like an honest response to a problem that intuition cannot solve. The confusion does not disappear, but it changes character. It becomes quieter, more reflective, less resistant. The story of how the parsec came to exist does not begin with a dramatic discovery or a sudden flash of insight. It begins, as many scientific ideas do, with irritation. A quiet, persistent irritation with numbers that were technically correct but practically useless. Astronomers in the 19th and early 20th centuries were not confused about what they were trying to measure. They were confused about how to talk about it in a way that matched what they were actually doing. By that point, the sky had already been mapped with remarkable precision. Positions of stars were catalogued. Their motions across the sky were tracked. Telescopes had grown powerful enough to reveal subtle shifts that earlier generations could not detect. Yet when it came to distance, language lagged behind technique. Astronomers could infer how far away stars were, but every time they tried to express those distances in familiar terms, the results felt clumsy. The irritation came from this mismatch. The method was elegant, the numbers were not. To understand why, it helps to picture what astronomers were actually measuring. They were not measuring distance directly. No one was sending out probes or bouncing signals off stars. Instead, they were measuring angles, tiny ones, almost insultingly small ones, fractions of a degree, changes in apparent position so subtle that they could only be detected by comparing careful observations made months apart. This technique, stellar parallax, had been discussed for centuries before it was successfully measured. The idea itself is simple. As Earth orbits the Sun, our viewpoint changes. Nearby stars should appear to shift slightly against the background of more distant stars. The closer a star is, the larger that shift should be. For a very long time, astronomers searched for this effect and failed to find it. The failure was not because the idea was wrong. It was because the stars were much farther away than anyone had expected. The angles involved were so small that even the best instruments of the time could not detect them reliably. When parallax was finally measured in the 1830s, it was a quiet triumph. No fireworks, no sudden rewriting of physics. Just a careful confirmation that the stars were staggeringly distant. The first successful measurements produced numbers that were almost comically small, fractions of an arcsecond, values that demanded precision bordering on obsession. And now the irritation returned in force. Astronomers could measure these angles, they could calculate distances from them. But expressing those distances in miles or kilometres resulted in unwieldy figures that obscured the very clarity the measurement provided. A star with a parallax of a fraction of an arc-second translated into trillions of kilometres. The calculation worked, but the expression felt disconnected from the observation. The unit did not reflect the method. This is an important point, because scientists are not just concerned with getting answers. They are concerned with communicating them efficiently, accurately, and in a way that preserves meaning. A unit that hides the relationship between measurement and result is a poor tool, even if it is technically sound. So instead of asking how to make the numbers smaller, astronomers asked a different question. What if the unit itself were defined by the measurement? This question led, slowly and without fanfare, to the parsec. The idea behind it is almost embarrassingly straightforward. If stellar distance is determined by measuring parallax, then why not define a unit of distance directly in terms of parallax? Instead of measuring an angle, converting it into a distance in kilometres, and then dealing with the resulting avalanche of zeros, why not let the angle itself define the unit? A parsec is the distance at which a star would have a parallax angle of 1 arc-second when observed from opposite sides of Earth's orbit. That is it. No embellishment, no metaphor, no reference to travel or time, just geometry. The name itself reflects this stripped-down approach. Parsec is short for parallax of 1 arc-second. It is a functional name, born from a calculation rather than a story. It was never meant to inspire, it was meant to simplify. This origin explains much about why the parsec feels the way it does. It was not designed with intuition in mind. It was designed to eliminate a step in the workflow of astronomers. Instead of saying, this star has a parallax of x arc-seconds which corresponds to y kilometres, they could simply say, this star is at a distance of 1 over x parsecs. The math becomes cleaner. The relationship becomes obvious. Double the parallax, halve the distance. Halve the parallax, double the distance. The inverse relationship between angle and distance is baked directly into the unit. From a practical standpoint, this was a quiet revolution. Distances to nearby stars could now be expressed in numbers that reflected measurement uncertainty naturally. A parallax of 0.5 arc-seconds corresponded to 2 parsecs. A parallax of 0.1 arc-seconds corresponded to 10 parsecs. The numbers stayed manageable. The connection between observation and inference remained visible, but practicality rarely translates into popularity. Outside astronomy, the parsec had no natural foothold. It did not relate to travel. It did not describe time. It did not map onto any human experience. It was a unit created by specialists for specialists, and it carried that origin openly. This is one reason it often feels opaque to newcomers. There is no intuitive ladder to climb. You either accept the definition or you don't. There is little in between. Historically, the parsec did not immediately replace other units. Astronomers continued to use astronomical units for solar system distances and light years for broader communication. The parsec gradually established itself where it was most useful, in the study of nearby stars and the structure of the Milky Way. As measurements improved, its usefulness expanded. Better telescopes meant more precise parallax measurements. Space-based observatories eliminated atmospheric distortion. Missions dedicated to astrometry refined stellar positions to astonishing accuracy. Each improvement reinforced the value of a unit tied directly to parallax. Over time, the parsec scaled naturally. Kiloparsecs became the language of galactic structure. Megaparsecs became the language of galaxy clusters and cosmic expansion. The unit that began as a convenience for nearby stars grew into a backbone of cosmological measurement. Yet its origin remained quietly geometric. There is something almost philosophical about this. The parsec does not define distance as an intrinsic property of space. It defines distance as something that emerges from perspective. Move the observer, and distance reveals itself through change. No movement, no measurement. In this sense, the parsec encodes a lesson about knowledge itself. It reminds us that understanding often depends not on reaching an object, but on shifting how we look at it. This lesson was not lost on astronomers, even if it rarely appeared in textbooks. The Parsec reinforced the idea that Earth is not a neutral vantage point. Our orbit matters, our motion matters. The fact that we are moving through space is not a complication to be corrected. It is a tool to be used. Without Earth's orbit, parallax would vanish. Without parallax, the parsec would be meaningless. The unit is inseparable from our planet's path around the Sun. That dependency adds another layer to its origin. The parsec is not just a cosmic unit. It is a local one, anchored to Earth's motion even as it describes stellar separation. It ties the vastness of space to the modest scale of an orbit. This grounding is subtle, but important. It keeps the parsec from becoming purely abstract. It is defined by something real and repeatable, something we can measure with increasing precision. Still, the origin of the parsec also explains why it resists casual explanation. It is born from a specific method, not from a desire to make the universe feel approachable. Its job is not to comfort. Its job is to clarify relationships that would otherwise be buried under unwieldy conversions. This clarity comes at a cost. The cost is familiarity. Unlike miles or light years, the parsec does not invite analogy. You cannot easily say how long it would take to cross one at a given speed without immediately abandoning the unit's original purpose. You can convert it, of course, but conversion is not the point. The parsec exists to keep distance tied to observation, not to movement. Understanding its origin helps soften this resistance. When you stop expecting the parsec to behave like an everyday unit, it becomes easier to accept it on its own terms. It stops being a strange alternative and becomes a natural expression of how distance is actually known. And this, perhaps, is the most curious part of its origin. The parsec was not invented to be clever. It was invented to be honest. Honest about what could be measured, honest about how it was measured, honest about the limits of intuition. In that honesty lies its quiet endurance. As astronomy continues to refine its measurements, as instruments grow more precise and surveys more comprehensive, the parsec remains embedded in the language of the field, not because it is elegant in a poetic sense, but because it aligns cleanly with the geometry of observation. And once you trace it back to that simple irritation, the desire to avoid drowning in zeros and conversions, the parsec's existence begins to feel less mysterious. It becomes a reminder that many of the strangest concepts in science are not born from grand theories, but from practical needs, slowly shaping language to fit reality rather than the other way around. From this point, the parsec no longer feels like an arbitrary invention. It feels like an inevitable one, waiting patiently for the moment when angles became measurable enough to demand a unit that spoke their language. The moment angles enter the conversation, distance begins to behave differently. It stops acting like a stretch you could cross and starts acting like a relationship you have to infer. This shift is easy to overlook because angles feel simple. We use them constantly without thinking. We glance left or right. We tilt our heads. We notice when something is slightly off-center. None of this feels mathematical. It feels instinctive. In astronomy, that instinct is pushed far beyond its comfort zone. When astronomers talk about angles, they are not talking about wide turns or obvious separations. They are talking about differences so small that they sit right at the edge of what instruments can reliably detect. Fractions of arc seconds, slivers of a degree that exist more as numbers than as sensations, and yet, these almost invisible angles carry the burden of revealing how the universe is arranged in 3 dimensions. This is where the dance begins. It is not a dramatic dance. There is no sudden movement, no sweeping arcs across the sky. It is slow, patient, repetitive. Earth moves, the stars appear to respond, then Earth moves again, and the pattern repeats. Over months, over years, the same subtle shifts accumulate into something meaningful. From the surface of Earth, the sky looks static. Stars rise and set. Constellations wheel overhead. But relative to one another, most stars appear fixed, locked into patterns that barely change over a lifetime. This apparent stillness is deceptive. It hides the fact that everything is in motion, including the observer. Earth does not sit still while observing the universe. It traces a wide, nearly circular path around the Sun once every year. That motion is smooth, predictable, and relentless. From one side of that orbit to the other, the observer's position changes by roughly 2 astronomical units. That baseline, modest by cosmic standards, is enormous compared to any measuring stick humans can physically deploy. Astronomy takes advantage of this. As Earth moves along its orbit, nearby stars appear to shift slightly against the background of more distant stars. This effect is parallax. It is the same phenomenon you can demonstrate by holding your finger out in front of your face and alternately closing one eye, then the other. Your finger jumps relative to the background, even though it has not moved at all. The jump is small, but it is real. In space, the background stars are so far away that their own parallax is negligible. They form a reference grid, a backdrop against which the motion of nearer stars can be measured. The closer a star is, the larger this apparent shift becomes. The farther away it is, the smaller the shift, until it vanishes into measurement noise. This relationship is beautifully simple, but simplicity does not make it easy. The angles involved are unimaginably tiny. 1 arcsecond is roughly the apparent size of a coin seen from several kilometers away. Measuring such a shift in a point of light requires extraordinary precision. It requires accounting for atmospheric distortion, instrument drift, and even the subtle wobble of Earth itself. Yet astronomers persist, because these angles are honest. They do not rely on assumptions about how bright or large a star should be. They emerge directly from geometry. The dance, then, is between Earth's orbit and the sky's apparent stillness. Earth moves, stars seem to slide. Earth continues, stars return to their original positions relative to the distant background. The motion traces out a tiny ellipse in the sky, the size of which encodes distance. This ellipse is not physical, it exists only in apparent position, but it is consistent, measurable, and repeatable. The brilliance of this method lies in its restraint. It does not ask stars to cooperate. It does not demand that they emit a certain amount of light or follow a particular pattern. It simply observes how they appear to behave when the observer moves. This is why angles matter so much. Distance becomes something you deduce from change rather than something you measure directly. The universe does not hand you a ruler. It hands you motion and perspective. The parsec, emerging from this method, is inseparable from the geometry of that motion. 1 parsec corresponds to a parallax angle of 1 arcsecond. That definition ties distance directly to the size of this annual dance. A star with a larger parallax is closer. A smaller parallax means greater distance. The inverse relationship is clean and unforgiving. What makes this dance subtle is not just the smallness of the angles, but the regularity of the motion. Earth's orbit provides a steady rhythm. 6 months apart, the observer reaches opposite sides of the orbit. The parallax shift reaches its maximum. In between, the shift traces a smooth curve. This rhythm allows astronomers to separate parallax from other motions. Stars are not truly fixed. They move through space. They have their own velocities, their own paths. Over time, these motions cause stars to drift slowly across the sky, a phenomenon known as proper motion. The parallax signal rides on top of this drift. Disentangling the two requires patience. Observations must be repeated over long periods. Patterns must be identified and isolated. The parallax effect repeats annually. Proper motion does not. By watching the sky long enough, astronomers can separate the cyclic dance from the steady march. This separation is delicate. It demands trust in the orbit, trust in the instruments, and trust in the mathematics that ties angle to distance. There is no shortcut. Each star must be watched, measured, and modelled individually. The result of this effort is not just a number, it is a relationship between Earth's motion and stellar position that remains valid regardless of what the star is doing internally. This is part of what makes parallax so powerful and so limited at the same time. It is powerful because it is direct. It is limited because the angles shrink rapidly with distance. Beyond a certain point, the dance becomes too subtle to detect, even with the best instruments. The stars stop responding visibly to Earth's motion, not because they are motionless, but because the baseline is too small relative to their distance. This limitation shaped the early map of the cosmos. For a long time, parallax could only be measured for relatively nearby stars. The rest of the universe remained dimensionless, its depth inferred indirectly. As instruments improved, the boundary pushed outward. Space-based observatories eliminated atmospheric interference. Detectors became more sensitive. The dance grew clearer. Even so, the principle remained unchanged. Distance emerged from angle. The parsec remained the natural unit. There is something quietly elegant about using Earth's orbit as part of the measuring apparatus. It turns a limitation into a feature. Instead of lamenting the fact that we cannot move freely through space, astronomers use the motion we already have. The orbit becomes a baseline that repeats endlessly, offering a built-in calibration. This elegance is easy to miss because the result feels abstract. We're used to thinking of orbits as paths objects follow. Here, the orbit becomes a measuring stick, not because of its size alone, but because of its regularity. Every year, the same motion repeats. Every year, the same angles can be measured again. Errors can be averaged out. Precision improves. The dance does not rush. It unfolds at the pace of the planet. There is also a philosophical undercurrent here that often goes unspoken. Distance, in this framework, is not an inherent property waiting to be discovered. It is something that emerges from comparison. Change the observer's position, and distance reveals itself through difference. This challenges a deeply ingrained assumption about space. We tend to think of distance as absolute, something that exists independently of how or from where it is measured. Parallax reminds us that measurement is relational. Without movement, without perspective, distance remains hidden. The parsec encodes this idea in its definition. It is not defined by how far light travels in a given time. It is not defined by a fixed length etched into the universe. It is defined by how much a star appears to move when the observer does. The dependence on motion gives the parsec a dynamic character, even though it describes static separation. It is a distance born from movement, inferred from change, stabilized through repetition. As you sit still listening to this, Earth continues its orbit. The baseline exists whether we pay attention to it or not. The dance goes on quietly, carrying with it the information needed to map the nearby universe. This perspective also explains why the parsec resists casual explanation. To understand it, you must accept that distance is not always something you can imagine stretching out in front of you. Sometimes it is something you detect by watching how the world shifts when you move. This idea becomes more comfortable with time. It stops feeling like a trick and starts feeling like a natural extension of how perception works. Your brain already uses parallax to judge depth. Astronomy simply scales that process up far beyond what your senses can handle unaided. The subtlety of the dance is not a flaw, it is the price of honesty. Rather than inventing assumptions about stellar brightness or size, astronomers let geometry do the work. Angles do not care what a star is made of, or how old it is, or how brightly it burns. They respond only to position. That impartiality is rare and valuable. As measurements improve, as the dance becomes easier to track across larger distances, the parsec remains rooted in the same simple geometry. It does not change its definition to accommodate new discoveries. It does not need to. It grows naturally with the precision of observation. And in that sense, the parsec is less a unit imposed on the universe and more a unit extracted from it. The dance of angles and orbits is always happening, whether or not we are watching. Earth traces its path. Stars trace their apparent ellipses. The geometry holds. The information is there, waiting to be measured. Understanding this does not suddenly make the parsec intuitive. It makes it honest. It reveals why this strange unit exists at all, and why it remains indispensable for making sense of a sky that refuses to sit still while we try to measure it. At some point, the idea quietly settles in that Earth is not just the place from which observations are made, but part of the observation itself. This is not obvious at first. We tend to imagine scientific instruments as separate things, devices we build, calibrate, and point outward. Telescopes, detectors, sensors. Earth, in that picture, is merely the platform beneath them. Solid, passive, uninvolved. But in astronomy, especially when it comes to distance, Earth refuses to remain passive. Long before space telescopes and digital detectors, astronomers realized that the planet they stood on was already doing something extraordinarily useful. It was moving. Not erratically, not unpredictably, but in a smooth, reliable path around the Sun. Year after year, without pause, Earth traced the same broad orbit, offering a built-in baseline that no human-made structure could rival. At first, this motion was an inconvenience. It complicated observations. It shifted the sky. It meant that stars did not sit still where you left them. But gradually, that inconvenience began to look like an opportunity. If Earth moves, then our viewpoint moves, and if our viewpoint moves, then nearby objects should appear to shift against distant ones. This is not a new insight. It is the same principle your brain uses to judge depth every time you move your head. The difference is scale. On Earth, parallax happens over the span of centimeters. In astronomy, it happens over hundreds of millions of kilometers. Once this realization took hold, Earth stopped being just the observer's home and became part of the measuring apparatus. The planet's orbit was no longer a nuisance to correct for. It was the ruler itself. This transformation in perspective was subtle but profound. Instead of asking how far away a star was in absolute terms, astronomers began asking how much that star appeared to move as Earth travelled from one side of its orbit to the other. The distance between those two observing points, roughly 2 astronomical units, became the baseline. The shift in apparent position became the signal. This is not a measurement you can feel. You cannot sense Earth's orbital motion in your body. You cannot look up and see the stars sliding back and forth over the course of a year. The movement is far too small, the sky far too vast. And yet, with careful instruments, the effect is there. That is what makes this method both elegant and unsettling. We're used to tools that are distinct from ourselves. A thermometer measures temperature. A scale measures weight. A ruler measures length. They sit outside the thing being measured. When Earth becomes the measuring tool, that separation collapses. The observer, the platform, and the instrument merge. The baseline is not something you hold, it is something you ride. Earth's orbit is not a straight line. It is an ellipse, close enough to circular that for most purposes the distinction barely matters. Over the course of 6 months, Earth moves from one side of this orbit to the opposite side. From those two positions, astronomers take measurements of stellar positions relative to distant background stars. The difference between those two measurements is the parallax shift. The geometry is straightforward, the execution is not. To extract meaningful information from this process, astronomers must account for a staggering number of variables. Earth does not orbit alone. It wobbles slightly due to the gravitational influence of other planets. Its axis tilts. Its rotation introduces additional motion. The atmosphere bends light. Instruments flex and drift. Even the stars themselves are moving. All of this must be disentangled from the parallax signal. This is why parallax measurements took so long to achieve and why they continue to improve with better technology. The effect is small, the noise is large, the patience required is immense. But once the signal is isolated, the reward is clarity. The parallax angle tells you how far away the star is, not because the star cooperates, but because Earth does. The planet's orbit provides a consistent, repeatable baseline. Every year, the same motion happens again. Errors can be averaged out. Confidence increases. This repetition is crucial. Without it, Earth would be a poor measuring tool. A one-time movement would not suffice. But the orbit repeats endlessly, offering astronomers as many opportunities as they need to refine their measurements. In this sense, Earth is a remarkably reliable instrument. It is also an instrument we did not design. We inherited it. This raises an interesting point about the nature of measurement in astronomy. Unlike laboratory sciences where conditions can be controlled and instruments adjusted at will, astronomy often relies on natural processes: planetary motion, atomic transitions, cosmic expansion. Instead of building everything from scratch, astronomers learn to use what the universe already provides. Earth's orbit is one of the earliest and most important examples of this approach. By using Earth as a measuring tool, astronomers tied their understanding of stellar distance directly to the structure of the solar system. The scale of the orbit becomes the foundation upon which larger scales are built. Astronomical units lead to parsecs, which lead to kiloparsecs and beyond. This layered structure is not arbitrary. It reflects the way knowledge grows outward from what can be measured directly. The Earth-Sun distance can be measured through radar ranging and celestial mechanics. That distance defines the astronomical unit. Earth's orbit, measured in astronomical units, defines the baseline for parallax. Parallax defines the parsec. The parsec defines larger cosmic distances through extension and modelling. Each step rests on the previous one. This chain of reliance is both a strength and a vulnerability. If the foundation were flawed, everything built upon it would wobble. That is why such care is taken in defining and refining these measurements. Precision at the local level matters enormously at the cosmic level. When Earth becomes a measuring tool, it also becomes a source of humility. The distances we infer depend on our position. They depend on our motion. They depend on our ability to measure angles with extraordinary precision. There is no pretense of omniscience here. Distance is not something we simply know. It is something we work out indirectly, with Earth doing much of the heavy lifting. This indirectness can feel unsatisfying, especially if you prefer clean, absolute answers. But it is also honest. It acknowledges that our access to the universe is mediated by where we are and how we move. There is no view from nowhere. Using Earth as a measuring tool also blurs the line between local and cosmic. The same orbit that governs seasons and calendars becomes the key to mapping the stars. The same motion that gives us years gives us parsecs. Time and distance intertwine quietly in the background. This intertwining is easy to miss because the parsec itself does not mention time explicitly. But Earth's orbit is a temporal process. It unfolds over a year. The parallax measurement is inseparable from that duration. You cannot measure it instantaneously. You must wait. You must observe. You must let the planet complete part of its journey. Distance in this sense is not just spatial. It is procedural. This procedural nature explains why parallax measurements improve slowly. They cannot be rushed. You cannot speed up Earth's orbit. You cannot compress 6 months into a weekend. The universe sets the pace, and astronomers adapt. This pacing has shaped the culture of astronomy in subtle ways. It rewards patience. It favours long-term projects. It encourages collaboration across generations. Data collected decades ago can still be valuable today because the underlying motion remains the same. When Earth is your measuring tool, time becomes part of your methodology. There is also something deeply grounding about this approach. Even as astronomers measure distances to stars hundreds of trillions of kilometers away, they do so using a motion that happens right beneath our feet. The cosmic and the local are linked by geometry. This link helps explain why the parsec, despite its abstract definition, remains rooted in something tangible. It is tied to Earth's orbit, not to an arbitrary length floating in conceptual space. The unit may feel strange, but its foundation is familiar. Earth circles the Sun. From that motion, distance emerges. This perspective also reframes how we think about our place in the universe. Earth is not just a tiny speck lost in vastness. It is an active participant in the process of discovery. Its motion, its position, its stability all contribute to our ability to understand what lies beyond it. This does not make Earth special in a mystical sense. It makes it useful. Other planets could, in principle, serve a similar role. A larger orbit would provide a larger baseline. A different vantage point would yield different measurements. Space-based observatories already extend this idea, using spacecraft motion to refine parallax further. But Earth remains the starting point. It is the first ruler, the first baseline, the original measuring tool. As technology advances, Earth's role does not disappear. It integrates with new tools. Space telescopes still rely on Earth-based calibration. Data still flows back to this planet. The orbit still matters. Understanding this helps demystify the Parsec. It stops being a bizarre, arbitrary unit and starts looking like the natural outcome of using Earth's motion as a measurement strategy. The unit reflects the method. The method reflects the planet. This is not something you need to hold actively in your mind. It can sit quietly in the background, like the knowledge that Earth is spinning even when you feel still. The measurement happens whether you think about it or not. Earth continues its orbit. Stars continue their subtle dance. Angles continue to encode distance. And as this process unfolds year after year, the universe slowly reveals its depth, not through dramatic gestures, but through the steady, patient motion of a planet doing exactly what it has always done. One of the most persistent misunderstandings about the Parsec is also one of the most revealing. People hear the word and instinctively place it in the wrong category. It sounds like it should belong with seconds, minutes, or years. It feels like it measures duration rather than separation. This confusion is so common that it has almost become part of the Parsec's identity, trailing behind it wherever it appears outside professional astronomy. This is not because people are careless or inattentive. It is because language quietly shapes expectation. We're used to units ending in certain sounds meaning certain things. Seconds tick, years pass, hours stretch and shrink depending on what we're doing. Even words like decade or century carry a strong sense of time flowing forward. When a word like parsec enters the conversation, especially in a scientific context, the brain reaches for familiar patterns. It hears something clipped, technical and abstract, and it associates it with timekeeping rather than distance. This instinct is reinforced by cultural exposure. Outside textbooks, parsecs most often appear in stories, films, and casual references to space. In those settings, they are rarely explained carefully. They are used as shorthand for very far or very impressive. Sometimes they are even used incorrectly, described as a measure of speed or duration. Each time this happens, the misunderstanding deepens, not because people are foolish, but because repetition creates familiarity. Over time, the parsec begins to feel like a time unit, simply because it often appears alongside talk of travel, journeys, and long spans. But the parsec stubbornly refuses to cooperate with this interpretation. At its core, a parsec has nothing to do with time passing. It does not describe how long something takes. It does not measure duration, delay, or sequence. It is indifferent to clocks. It does not care how fast or slow anything moves. It exists entirely in the domain of geometry. Understanding why requires stepping back and looking at how we usually distinguish time from distance. Time units describe change. They measure how long something lasts, how long it takes for one event to follow another, or how long a process unfolds. Distance units describe separation. They measure how far apart 2 points are, regardless of whether anything moves between them. On Earth, these two categories often blur together because movement is common and speeds are relatively consistent. If you know how fast something moves, you can convert distance into time or time into distance without much trouble. Walk for an hour and you will cover a certain distance. Drive for 10 minutes and you will cover another. This easy convertibility trains the brain to treat distance and time as interchangeable in everyday thinking. Space disrupts this habit almost immediately. In space, speeds vary wildly. Objects move under the influence of gravity, inertia, and expansion. Light moves at a constant speed in a vacuum, but almost nothing else does. Even when light is involved, the scale is so large that everyday intuition collapses. The Parsec does not attempt to preserve this fragile link between time and distance. It severs it cleanly. A parsec does not tell you how long light takes to travel that distance, even though such a calculation can be done. It does not tell you how long a spacecraft would need, even hypothetically. It does not care about velocity at all. It exists as a statement of separation, not of journey. This is why it is so often confused with a time unit. We're used to thinking about cosmic distances in terms of how long something would take to cross them, because crossing is how we understand distance locally. The Parsec refuses to engage with that framing. It does not answer the question we instinctively ask. Instead of asking, how long would it take to get there? The Parsec answers a different question entirely. It answers, how does this object appear to move when the observer changes position? That question has no temporal component in its definition. Yes, the observation takes time. Earth's orbit unfolds over months. Measurements are taken across a year, but the unit itself does not encode that duration. It encodes the geometry of the situation, not the timeline of the observation. This distinction is subtle, and it is often lost in casual explanation. Part of the confusion also comes from the presence of the word second in the parsec's origin. An arcsecond is an angular measurement, not a unit of time, but the word itself sounds temporal. Historically, this is no accident. Degrees, minutes, and seconds of arc borrow their names from timekeeping, because both systems divide circles into familiar fractions. A circle can be divided into degrees, each degree into minutes, each minute into seconds. These are angles, not durations, but the shared terminology invites misunderstanding. When someone hears that a parsec is defined using an arcsecond, the confusion compounds. Seconds sound like time. Parsec sounds like time. The brain connects the dots incorrectly. In reality, the arcsecond in question is a tiny slice of angle, not a tick of a clock. It measures how far apart two lines of sight are, not how long anything lasts. The parsec inherits this angular ancestry, even if the language obscures it. Another reason the parsec is mistaken for a time unit is that it often appears alongside the light year, which does explicitly reference time in its name. A light year is a distance defined by how far light travels in 1 year. It is a distance unit that borrows temporal language for convenience. The parsec does not do this. Where the light year uses time to define distance, the parsec uses geometry. One relies on speed and duration. The other relies on angle and baseline. They arrive at similar scales, but through entirely different conceptual routes. This difference matters more than it first appears. When you define distance using time, you implicitly prioritize motion. You imagine something moving from one place to another. When you define distance using angle, you prioritize perspective. You imagine yourself moving and watching how the world shifts in response. These are not interchangeable ways of thinking. They lead to different intuitions, different mistakes, and different insights. The parsec belongs firmly to the second category. It describes distance as something revealed through relative change in viewpoint, not as something traversed. This is why it feels disconnected from time. It is not meant to be experienced as duration. It is meant to be inferred as a spatial relationship. This becomes clearer if you imagine a frozen universe. Imagine that nothing moves except Earth's orbit. Stars are fixed. Light behaves normally. You observe a nearby star from one side of the orbit, then from the other. You measure its parallax. You calculate its distance in parsecs. Now imagine stopping time entirely. Freeze everything. The distance to the star does not change. The parsec still describes that separation. Time passing was necessary to make the measurement, but it is not part of what the measurement describes. This is the key distinction. Time is a tool in the process, not a property of the result. In everyday life, we often conflate the two because the process and the result are tightly linked. You measure distance by moving through it. You measure time by waiting. In astronomy, especially at stellar scales, the process and the property decouple. You can know a distance without ever imagining a journey. This decoupling is uncomfortable at first. It asks you to let go of a deeply ingrained habit of thought. It asks you to accept that distance does not owe you a travel narrative. The parsec is indifferent to stories. It does not tell you what it would be like to go somewhere. It does not suggest effort, difficulty, or duration. It simply states a fact about spatial arrangement derived from geometry. This is why correcting the misconception matters, even if it feels pedantic. Calling a parsec a time unit is not just a minor error. It changes the entire framing of what the unit represents. It shifts attention away from perspective and toward motion, away from geometry and toward narrative. Once that shift happens, the parsec becomes harder to understand, not easier. There is also a deeper philosophical reason why the parsec resists being treated as time. Time, as we experience it, has direction. It flows. It has a before and after. Distance does not. Two objects can be separated by a parsec without implying any sequence. One does not come before the other. They simply are. By grounding distance in angle rather than duration, the parsec keeps itself free of temporal implication. It does not suggest change. It suggests relationship. This neutrality is valuable in astronomy, where time behaves in strange ways. Relativity complicates simultaneity. Different observers experience time differently depending on motion and gravity. Anchoring distance too closely to time can introduce conceptual pitfalls. The parsec avoids these pitfalls by staying in its lane. It is a unit that remains valid regardless of how time behaves locally. It does not depend on clocks running at the same rate everywhere. It does not depend on light behaving differently in different reference frames. It depends only on geometry and perspective. This robustness is one reason it remains so useful in professional contexts, even if it feels awkward in casual conversation. There is a quiet irony here. The parsec is often mistaken for a time unit precisely because it strips time out of distance so thoroughly. It feels abstract, detached, and technical, qualities we often associate with timekeeping at large scales. Meanwhile, the light year, which explicitly uses time in its definition, feels more intuitive. This inversion says more about human intuition than about the units themselves. We like distance to feel like duration. We like to imagine journeys. We like to turn separation into stories. The parsec does not indulge that preference. It insists on a different way of knowing. Once you accept that insistence, the confusion begins to fade. The parsec stops feeling like a mislabeled second and starts feeling like what it is, a compact way of expressing how space reveals itself when you move within it. It becomes a statement about observation rather than experience. This does not mean you have to stop using light years or imagining travel. Those metaphors have their place, but they are metaphors. The parsec is a measurement. Understanding why it is not a unit of time helps clarify what it is trying to do and why it sounds the way it does. It was never meant to sound comforting. It was meant to be precise. And precision, especially when it refuses to tell a story, often sounds strange to ears trained on narrative. The parsec becomes less confusing, not because it becomes familiar, but because it becomes honest. It stops pretending to answer questions it was never designed to answer. It stops being mistaken for something it is not. What remains is a unit that quietly does its job, indifferent to clocks, journeys, and impatience, describing separation in a universe where time and distance do not always cooperate in ways we expect. The moment light years enter the conversation, something curious happens to understanding. On the surface, light years feel helpful. They sound explanatory. They seem to offer a bridge between the vastness of space and the everyday experience of time passing. Light moves fast. A year is familiar. Put them together, and the distance suddenly feels interpretable, or at least narratable. You can imagine light leaving a star, travelling for years, and finally arriving here. There is a story built into the unit. Parsecs do not offer that story. This difference alone has created decades of quiet misunderstanding, not just among casual listeners, but sometimes even among people who feel reasonably comfortable with science. Light years feel like they're doing explanatory work. Parsecs feel like they are withholding it. And when two units describe similar scales but behave so differently in language, confusion is almost guaranteed. At first glance, light years and parsecs appear to be rivals. Two ways of measuring the same thing. Two languages describing the same reality. But the rivalry is mostly imagined. In practice, the two units answer different needs, serve different habits of thought, and emerge from different questions. Understanding the misunderstandings between them requires looking at why light years became popular in the first place. Light years are, in a sense, a translation unit. They take a cosmic distance and translate it into a duration, something humans instinctively understand. Even if you cannot imagine light racing through space, you know what a year feels like. You know its rhythm. You know its length relative to your life. When you hear that a star is 10 light years away, you may not feel the distance spatially, but you feel the time. 10 years is something you can place emotionally. That emotional placement is powerful. It gives the illusion of understanding, even when the spatial reality remains abstract. Light years do not make space smaller or simpler. They make it more relatable. They allow distance to borrow familiarity from time. Parsecs refuse this borrowing. They do not translate distance into experience. They do not ask you to imagine travel or waiting. They remain stubbornly spatial, defined by angles and baselines rather than journeys and durations. This makes them feel colder, more technical and less welcoming. And yet, in professional astronomy, parsecs are often preferred. This preference is not arbitrary. It arises because light years, despite their intuitive appeal, hide important information. They tell you how long light would take to travel a distance, but they do not tell you how that distance was measured. They imply motion where none is required. They quietly suggest that distance is best understood as something traversed. In astronomy, traversal is often irrelevant. Most of the time, astronomers are not interested in how long something would take to get from one place to another. They're interested in how objects are arranged, how structures are shaped, and how distances relate to observable effects. For those purposes, a unit tied to observation rather than motion is more useful. The parsec encodes its measurement method directly into its definition. It tells you implicitly that this distance comes from parallax, from Earth's motion, from angles measured against a distant background. That information is absent in the light year. This absence is one source of misunderstanding. People often assume that light years are somehow more fundamental because they involve light, which feels fundamental. Light is fast, light is constant, light underpins much of modern physics. Surely a unit based on light must be superior, but superiority depends on context. A light year is defined as the distance light travels in 1 year in a vacuum. That definition assumes you know the speed of light and the length of a year. Both are well defined. The unit is precise, but it does not correspond to a direct measurement technique for most astronomical objects. It is usually derived after the fact by converting from another measurement. Parsecs, by contrast, fall directly out of the measurement process for nearby stars. Measure the parallax. Take the inverse. You have the distance in parsecs. No intermediate story about light travelling anywhere is required. This efficiency matters when precision matters. Another misunderstanding arises from scale. Light years are often used in popular explanations for large distances. Parsecs are often used in technical contexts. This division creates the impression that parsecs are only for professionals, while light years are for everyone else. Over time, this impression hardens into a false hierarchy. In reality, both units describe the same physical separations. One parsec is about 3.26 light years. Neither unit is more real than the other. They are simply different lenses. The misunderstanding lies in assuming that the more familiar lens is also the more accurate or meaningful one. Familiarity does not guarantee clarity. Light years encourage people to think of space as something light travels through like a road. Parsecs encourage people to think of space as a geometric structure revealed through perspective. Neither picture is wrong, but they emphasize different aspects of reality. Problems arise when these pictures are mixed carelessly. For example, people often hear statements like, "The galaxy is 100,000 light years across," and then imagine light travelling from one side to the other as if that journey were the point. The journey is not the point. The structure is. The arrangement of stars, gas, and dust is what matters. The light-year phrasing can distract from that. Similarly, when parsecs appear in popular media without explanation, they feel alien and unnecessary. Viewers wonder why a simpler unit was not used. They suspect pretension rather than precision. This suspicion is understandable but misplaced. Another layer of misunderstanding comes from the way these units interact with scale prefixes. Kiloparsecs, megaparsecs, gigaparsecs. These words stack unfamiliarity on top of unfamiliarity. Each prefix multiplies the distance, but the intuition does not scale with it. Light years suffer from the same problem at large scales, but their narrative framing delays the collapse of intuition slightly. Eventually, both units fail the imagination. At millions of light years or megaparsecs, neither unit helps you feel the distance. Both become labels. At that point, the choice of unit is driven almost entirely by convenience and convention. In cosmology, megaparsecs dominate because they integrate naturally with equations describing expansion, density, and structure. In stellar astronomy, parsecs dominate because they tie directly to parallax. Light years often appear in outreach because they sound explanatory. Misunderstanding arises when people assume these choices are aesthetic rather than functional. There is also a subtle conceptual misunderstanding baked into the light year itself. Because it is defined by how far light travels in a year, it invites people to think of distance as something inherently linked to time. This reinforces the habit of equating far with long ago. While there is a sense in which this is true, because light takes time to travel, it can lead to oversimplification. Distance and time are related, but they are not the same thing. A star can be distant without implying anything about when events occurred there, except in the limited sense of light travel delay. The parsec avoids this entanglement. It describes where things are arranged, not when their light left. This difference becomes important when discussing structures rather than events. When mapping a galaxy, the concern is spatial distribution, not light travel storytelling. Parsecs support that focus more cleanly. Another source of confusion is conversion. Because parsecs and light years convert cleanly into each other, people assume they are interchangeable in all contexts. Technically, they are. Conceptually, they are not. Choosing a unit shapes the questions you ask. If you describe a distance in light years, you're inviting questions about travel time, communication delay, and historical observation. If you describe it in parsecs, you're inviting questions about geometry, structure, and measurement uncertainty. Neither invitation is wrong, but mixing them without awareness leads to muddled thinking. This muddling is amplified in science fiction, where units are often used for dramatic effect rather than clarity. Parsecs are sometimes used incorrectly as measures of speed. Light years are sometimes treated as travel durations rather than distances. These mistakes seep into public understanding, not because fiction is persuasive, but because repetition normalizes error. Over time, these normalized errors become misconceptions that feel resistant to correction. The parsec suffers especially from this because it lacks a built-in story. It cannot defend itself with intuition. It requires explanation. When explanation is absent, misunderstanding fills the gap. But there is a quieter misunderstanding as well, one that affects even careful listeners. People often assume that because light years feel intuitive, they must be closer to how space really is. They treat parsecs as artificial constructs layered on top of reality. In fact, both units are constructs. Neither exists independently of definition. Reality does not come labelled in light years or parsecs. What differs is how closely a unit aligns with the method by which knowledge is obtained. Parsecs align closely with observation. Light years align closely with storytelling. This does not make one superior. It makes them suited to different purposes. When this distinction is missed, debates arise that are not really about measurement at all, but about comfort. People defend the unit that feels better, not the one that fits the task. Understanding this dissolves much of the tension. Light years are excellent for communicating vastness in a way that resonates emotionally. Parsecs are excellent for working with data and structure. Confusion arises when one is expected to do the other's job. The universe does not care which unit you use, but your understanding does. Once this becomes clear, the so-called rivalry between light years and parsecs fades into something quieter. They become complementary rather than competitive. Different dialects of the same language, each emphasizing a different aspect of reality. The misunderstandings persist mostly because the distinctions are rarely made explicit. People are taught the definitions but not the motivations. They learn what the units are, but not why they exist side by side. And without the why, the what feels arbitrary. As you sit with this, it becomes easier to see parsecs not as obscure or pretentious, but as honest reflections of how astronomers actually work. Light years remain useful, comforting, and evocative. Parsecs remain precise, geometric, and restrained. The misunderstanding dissolves not when one unit replaces the other, but when each is allowed to be what it is. Distance does not need a single language. It needs the right one for the question being asked. Once the initial confusion fades, once the parsec stops feeling like an unnecessary complication and starts feeling like a deliberate choice, a more practical question quietly takes its place. What do astronomers actually do with this distance? Not in theory, not in definitions, but in day-to-day work, in real observations, in the slow accumulation of knowledge about where things are and how they relate to one another. The answer is less dramatic than you might expect. There are no grand announcements every time a parsec is used. No sense of strangeness accompanies it once you're immersed in the practice. It becomes ordinary. It becomes background. And that ordinariness is precisely the point. Astronomers use parsecs the way builders use levels, or musicians use tuning forks. Not because they are interesting objects in themselves, but because they quietly enforce consistency. They keep measurements aligned with reality as it can actually be observed. The first and most straightforward use of the parsec is in mapping nearby stars. When astronomers measure stellar parallax, the raw result is an angle. That angle, measured in arcseconds, immediately translates into distance in parsecs through a simple inverse relationship. If the parallax is 1 arcsecond, the distance is 1 parsec. If the parallax is half an arcsecond, the distance is 2 parsecs. If the parallax is 1/10 of an arcsecond, the distance is 10 parsecs. This simplicity matters more than it seems. Astronomical data is noisy. Measurements come with uncertainty. Instruments drift. Background stars are not perfectly fixed. Atmospheric effects distort signals. When astronomers work with parallax data, they need a unit that reflects this uncertainty cleanly, without layering unnecessary complexity on top. Parsecs do that. Because the distance in parsecs is directly tied to the measured angle, the uncertainty in the angle translates naturally into uncertainty in distance. Error bars behave predictably. Statistical analysis becomes cleaner. There is no need to constantly convert between angular measurements and linear ones in kilometers or miles, dragging huge numbers and rounding errors along for the ride. This is not about convenience alone, it is about preserving meaning. When a star's distance is reported as, say, 12.4 parsecs with a certain uncertainty, another astronomer immediately understands how that number was obtained and what its limitations are. The unit itself carries methodological information. It signals that the distance likely comes from parallax, or from methods calibrated against parallax. That signal is lost if the same distance is expressed only in light years. Beyond nearby stars, parsecs become part of a ladder. Astronomers often speak of the cosmic distance ladder, a sequence of methods used to measure distances at increasing scales. Parallax sits at the bottom of this ladder. It is the most direct method. It does not rely on assumptions about intrinsic brightness or physical properties of objects. It relies only on geometry. Because of this, parallax distances expressed in parsecs are used to calibrate other distance indicators. For example, certain types of stars have predictable relationships between their brightness and other properties. If you know how bright such a star truly is, and you measure how bright it appears, you can infer its distance. But to know how bright it truly is, you need a sample of such stars whose distances are already known. Those anchor distances come from parallax. They are expressed in parsecs. Without parsecs, the ladder becomes shaky. Each rung depends on the one below it. If the foundation is poorly defined or inconsistently expressed, errors propagate upward. Parsecs provide a stable base because they are tied directly to measurement rather than inference. As astronomers move outward, parsecs scale naturally. Distances within the Milky Way are often expressed in kiloparsecs. The diameter of the galaxy is on the order of tens of kiloparsecs. The distance from the Sun to the galactic centre is about 8 kiloparsecs. These numbers are not chosen arbitrarily. They reflect the structure of the galaxy as it is observed and modelled. Using kilometres for this would be possible, but deeply impractical. Using light years would be fine, but it would obscure the connection to the measurement techniques used to derive those distances. Kiloparsecs fit neatly into equations describing galactic dynamics, mass distribution, and rotation curves. Astronomers are not trying to make the galaxy feel approachable, they are trying to make it computable. At even larger scales, parsecs continue to dominate. When studying clusters of galaxies, large-scale structure and cosmic expansion, distances are often expressed in megaparsecs. This is not because megaparsecs are intuitive, but because they integrate smoothly with the mathematics of cosmology. Key quantities such as the expansion rate of the universe are often expressed in units that involve megaparsecs. Densities, correlation lengths, and clustering scales all make sense in this framework. The unit becomes part of the language of the equations themselves. This is one of the most important ways astronomers actually use parsecs. They build them into models. When a model describes how matter is distributed across space, or how galaxies cluster, or how expansion stretches distances over time, parsecs provide a consistent spatial scale. They allow different observations to be compared directly. Data from different instruments, surveys, and epochs can be aligned because they speak the same unit language. This alignment is crucial in a field where no single observation tells the whole story. Another practical use of parsecs is in cataloguing and classification. Large surveys of stars and galaxies often define samples based on distance. For example, astronomers might study all stars within a certain number of parsecs from the Sun to understand local stellar populations. They might define a volume-limited sample, out to say, 100 parsecs to avoid biases introduced by brightness limits. Using parsecs in this context is not about drama, it is about clarity. The boundary of the sample corresponds directly to parallax measurement limits. It reflects what can be measured reliably. It ensures that the sample is complete within that volume. These considerations are central to statistical astronomy. Parsecs also appear in discussions of stellar environments. The density of stars, the frequency of certain types of systems, and the likelihood of interactions all depend on how many stars occupy a given volume of space. Expressing that volume in cubic parsecs keeps the numbers manageable and meaningful. Again, this is not something light years do particularly well in practice. When astronomers discuss interstellar phenomena such as gas clouds, star-forming regions or supernova remnants, parsecs provide a convenient scale. These structures often span fractions of a parsec to tens of parsecs. Expressing their size in kilometers would be absurd. Expressing it in light years would be fine, but parsecs align better with the observational data and the conventions of the field. Even when astronomers talk to one another informally, parsecs slip into conversation without ceremony. They are not announced or justified, they are assumed. This assumption is not elitism, it is efficiency. Everyone involved understands what a parsec implies. Importantly, astronomers do not expect parsecs to be intuitive. They do not need them to be. Intuition is not the goal in technical work. Consistency is. This is a point that is often missed in popular discussions. People sometimes criticize parsecs for being confusing, as if clarity to the uninitiated were the primary criterion for a scientific unit. It is not. The primary criterion is whether the unit supports accurate, reproducible work. Parsecs do. This does not mean astronomers avoid light years entirely. They switch units depending on audience and purpose. When communicating with the public, light years often appear because they provide an entry point. When writing papers, parsecs dominate because they integrate better with data and theory. This flexibility is a strength, not a contradiction. Understanding how astronomers actually use parsecs also reveals why the unit has survived despite its reputation. If parsecs were merely historical artifacts or aesthetic preferences, they would have been replaced. Science is ruthless about discarding tools that do not earn their keep. The parsec earns its keep every day. It shows up in star catalogues. It shows up in models of galactic structure. It shows up in discussions of stellar neighborhoods and cosmic surveys. It quietly supports the entire framework of distance measurement without demanding attention. There is also a subtle psychological effect at work. For astronomers, parsecs help keep thinking anchored in observation rather than imagination. They discourage storytelling. They encourage precision. When you work with parsecs, you are constantly reminded that distance is something inferred from geometry, not experienced as a journey. This reminder matters in a field where imagination can easily outrun evidence. By using parsecs, astronomers discipline their thinking. They stay close to what can be measured, what can be tested, what can be refined. The unit itself reinforces that discipline. Over time, this becomes second nature. The parsec stops being strange. It becomes invisible. This invisibility is the mark of a successful tool. The distance that once felt impossible becomes routine, not because it suddenly makes sense to human intuition, but because it fits seamlessly into the work that needs to be done. Astronomers do not need the universe to feel small. They need it to be describable. Parsecs help make that possible. As you sit with this, it becomes clear that the parsec's value lies not in its ability to impress or confuse, but in its quiet utility. It is used not because it sounds scientific, but because it removes friction from the process of understanding where things are and how they relate. In that sense, the parsec is not an obstacle to comprehension. It is a scaffold. It holds up the structure of astronomical knowledge while remaining mostly out of sight, doing exactly what it was designed to do. Trying to ask what a parsec feels like is already an unusual move, because the parsec was never designed to be felt. It was not built to fit inside the body, or the imagination, or the rhythms of daily life. It does not correspond to effort, endurance, or duration. And yet the question keeps returning, quietly and persistently, because humans are pattern-seeking creatures. We want to know where we stand in relation to things, even when those things are far beyond standing distance. So when we ask what a parsec feels like compared to human scale, what we are really asking is how to place something that resists placement into a mental world built from steps, rooms, streets, and horizons. On human scale, distance is intimate. It is measured in the reach of an arm, the length of a room, the walk to a nearby shop. Even when distances grow larger, they remain anchored to bodily reference. A kilometre is how long it takes to walk briskly. 10 kilometres is a run or a long bike ride. 100 kilometres is a drive that changes scenery. At every step outward, the body remains involved. A parsec removes the body entirely. There is no human action that corresponds to a parsec. No amount of walking, driving, or flying accumulates meaningfully toward it. Even the fastest machines we have built barely make a dent. The parsec sits so far beyond human effort that effort itself becomes irrelevant. This irrelevance is what makes the parsec feel alien. To make this more concrete, it helps to start very small and build upward slowly, even though the building process will eventually fail. That failure is part of the experience. Imagine standing in a room. The distance from one wall to the other is a few meters. You can cross it in seconds. Your brain understands this without calculation. It knows how much space that is because it has lived in spaces like it before. Now imagine a city, a few kilometers across. You cannot cross it instantly, but you can imagine doing so. The city has texture, streets, landmarks. Distance still behaves. Now imagine a country, hundreds or thousands of kilometers. You may not have crossed it on foot, but you have seen maps. You understand that it takes hours or days to traverse. Distance stretches, but it does not break. Now imagine the Earth itself, about 40,000 kilometers around. At this point, the body starts to retreat from the picture. You rely on abstractions, maps, flights, satellites. Still, Earth remains a place you can imagine as a whole. Now imagine the distance to the Moon, nearly 400,000 kilometers. This is where imagination begins to thin. You cannot picture the space between Earth and the Moon easily. It is mostly empty. But you can still imagine the two objects. The gap feels large, but not incomprehensible. Now imagine the distance to the Sun. About 150 million kilometers. At this scale, everyday intuition gives up. The numbers are known, but the space itself becomes a blank. You know the Sun is far away, but you cannot feel how far. You rely on diagrams and trust. Now imagine the distance to the nearest star beyond the Sun. This is where the idea of human scale quietly collapses. The nearest star system is more than 4 light-years away. In kilometers, that number is so large that it loses descriptive power. In parsecs, it is just over one parsec. That is all it takes to leave the solar system so completely behind that everything you know about distance stops working. This is the moment where the parsec reveals its emotional character, not through sensation, but through absence. It feels like nothing, because there is nothing to feel. There are no landmarks between stars that the human mind can hold on to. There is no gradual transition from one environment to another. There is only emptiness, punctuated by objects so far apart that their separation becomes the dominant feature. A parsec, compared to human scale, is not large in the way a mountain is large. It is not large in the way an ocean is large. It is large in the way silence is large. It is the absence of reference. This is deeply uncomfortable for the mind. Humans rely on intermediate structure to understand scale. We understand cities because they contain neighborhoods. We understand countries because they contain cities. We understand planets because they contain landscapes. A parsec contains almost nothing. Even when there are stars within a parsec of each other, the space between them is still overwhelmingly empty. The parsec is not a container full of things. It is mostly the space where nothing happens. This emptiness is what breaks intuition. When people try to imagine a parsec by compressing it into something familiar, the results are always unsatisfying. You can say that if the Earth were the size of a grain of sand, the nearest star would be kilometers away. You can scale the solar system down to a coin and place the next star across a city. These analogies are clever, but they do not translate into feeling. They remain intellectual exercises. The body remains uninvolved. This is why the parsec never quite settles into the imagination. It does not invite empathy. It does not suggest struggle or movement. It simply sits there, indifferent to human scale. And yet, astronomers work with parsecs constantly, which raises an interesting point. They are not immune to this disconnect. They do not feel parsecs either. They work with them abstractly, relationally, mathematically. Feeling is not part of the job description. This is an important realization. The discomfort you feel when trying to imagine a parsec is not a failure. It is an accurate response to something that exists outside the range of embodied understanding. The parsec is not meant to be felt. It is meant to be used. Compared to human scale, the parsec does not feel large. It feels distant from feeling itself. There is also a psychological effect at play here. Humans are very good at relative comparison within familiar ranges, but very bad at absolute comparison across radically different scales. The difference between 1 meter and 10 meters feels significant. The difference between 1 trillion kilometers and 10 trillion kilometers does not. A parsec lives entirely in this flattened zone of perception. When you say that one star is 3 parsecs away and another is 10 parsecs away, the difference sounds modest. But in human terms it represents a gulf so vast that it renders travel, communication, and even imagination irrelevant. The numbers compress emotional response rather than expand it. This compression is often mistaken for coldness or abstraction, but it is simply a consequence of scale. Another way to approach human scale is to think in terms of time, even though the parsec itself is not a time unit. Light takes more than 3 years to cross 1 parsec. That fact is often used as a proxy for feeling, because years are familiar. But even this approach quickly breaks down. 3 years is not a long time in human terms. You can remember where you were 3 years ago. You can imagine waiting 3 years. That does not feel overwhelming. But light travelling for 3 years, without stopping, without slowing, without encountering anything substantial, through a vacuum that barely contains a single atom per cubic meter, does not map onto human experience. The time feels small, the space does not. This mismatch creates cognitive dissonance. You're told that something both is and is not enormous, depending on which frame you use. The parsec exposes this mismatch rather than hiding it. In that sense, the parsec is honest in a way human-scale analogies are not. It does not pretend that distance can be translated into feeling. It allows the gap to remain. There is also something humbling in this gap. Human scale is not the default scale of the universe. It is a local accident shaped by biology, gravity, and environment. The parsec reminds us that most of reality operates outside that narrow window. Distances are not designed to be comfortable. When you stop trying to force the parsec into human scale, something interesting happens. It stops feeling frustrating and starts feeling neutral. It becomes just another coordinate, another way of organizing information. The question shifts from what does this feel like to what does this relate to? A star at 1 parsec is close, astronomically speaking. A star at 10 parsecs is part of the local neighborhood. 100 parsecs begins to sample a broader region of the galaxy. These distinctions matter scientifically, even if they do not matter emotionally. This is where the parsec begins to make peace with human thinking, not by becoming intuitive, but by becoming contextual. You do not need to feel a parsec to understand its role. You only need to know how it compares to other parsecs. This relational understanding is how astronomers operate. They rarely think in terms of absolute scale. They think in terms of structure, distribution, density. A cluster spans this many parsecs. A cloud extends that far. A region is sparse or crowded by parsec standards. Human scale falls away. A different scale takes over. From that perspective, the parsec does not feel large or small. It feels appropriate. There is also a subtle emotional shift that can occur if you sit with this long enough. The failure to imagine a parsec stops being a problem and becomes a quiet relief. You're not required to internalize it. You're allowed to let it exist outside you. This is different from many other concepts, which demand assimilation. The Parsec demands acceptance instead. Acceptance that the universe is not obligated to align with human sensation. Acceptance that some distances are not meant to be crossed, pictured, or felt. Acceptance that knowledge does not always come with comfort. In this sense, the Parsec compared to human scale feels like a boundary. Not a physical boundary, but a cognitive one. It marks the edge of embodied understanding and the beginning of abstract comprehension. That boundary is not a failure, it is a feature. The Parsec lives on the other side of it, doing its quiet work, indifferent to whether it feels like anything at all. And once you stop insisting that it should, it becomes easier to let it sit there, unbothered, as part of a universe that was never built around human proportions in the first place. When astronomers talk about stars that are only a few parsecs away, the word only does a great deal of quiet work. In everyday language, only suggests closeness, convenience, maybe even familiarity. Only a few minutes away, only a short walk, only across the street. But in astronomical language, only a few parsecs is a phrase that compresses an enormous gulf into something that feels almost neighbourly, at least by cosmic standards. This shift in meaning can be disorienting. A few parsecs is still far beyond anything human scale can comfortably hold, yet within astronomy it represents the immediate environment of the Sun, a region where individual stars can be catalogued, studied in detail, and compared carefully. It is the difference between knowing a face in a crowd and knowing that a crowd exists somewhere beyond the horizon. The stars within a few parsecs of Earth form what is often called the solar neighbourhood, not because these stars orbit the Sun, but because they share a region of space close enough that parallax measurements are strong, uncertainties are relatively small, and individual properties can be examined with confidence. This neighbourhood is not crowded in any everyday sense, it is staggeringly sparse. Even here, where stars are considered close, the distances between them are vast, and the emptiness between them dominates everything. Understanding this neighbourhood helps ground the Parsec in something slightly more concrete, not by making it feel small, but by showing how astronomers use it to define proximity in a universe where proximity itself is an unusual condition. Within 1 parsec of the Sun there are no stars. That fact alone is often surprising. The Sun's nearest stellar neighbour lies just over 1 parsec away. This means that even in what we call the immediate vicinity, there is nothing but interstellar space for more than 3 light-years in every direction. The solar system is not nestled among stars, it is isolated. This isolation is important. It means that when astronomers refer to stars a few parsecs away, they are talking about the very first layer of stellar surroundings beyond this isolation. These are the stars whose distances can be measured with the highest precision. Their positions, motions, and properties form the baseline for understanding stellar populations more broadly. At a few parsecs, parallax angles are relatively large by astronomical standards. They are still small in absolute terms, but they are measurable with confidence. This makes these stars the anchors of distance measurement. They are the points against which other methods are calibrated. Stars in this range are often studied repeatedly over long periods. Their motions across the sky, their subtle wobbles caused by unseen companions, their brightness variations and their spectra are all monitored carefully. Because their distances are well known in parsecs, astronomers can translate observed properties into intrinsic ones with less ambiguity. This is where the Parsec becomes practical rather than philosophical. Knowing that a star is, for example, 5 parsecs away allows astronomers to calculate its true luminosity from its apparent brightness. It allows them to estimate its size, its mass, and its stage in stellar evolution. These calculations depend critically on distance. Small errors propagate into large uncertainties if distance is poorly known. Stars that are only a few parsecs away minimize those errors. This is why so much attention is given to them, even though they are relatively unremarkable in many other respects. Most nearby stars are small, dim, and red. They are not the bright, massive stars that dominate the night sky. They are easy to overlook visually, but scientifically, they are invaluable. They form a representative sample of what stars in the galaxy are actually like. The brightest stars you see with the naked eye are not typical. They are bright because they are either unusually luminous or unusually close, or both. The stars within a few parsecs reveal the quieter reality. They show that the galaxy is dominated by small, long-lived stars that burn slowly and steadily. This realization emerged gradually as nearby stars were catalogued and studied. Early astronomers, limited by brightness and distance uncertainties, naturally focused on what they could see easily. As parallax measurements improved, the picture changed. The solar neighborhood turned out to be populated mostly by stars that barely announced themselves. Parsecs made this discovery possible. By defining a volume of space in parsecs and studying everything within it, astronomers could construct a volume-limited sample. This means that instead of selecting stars based on how bright they appear, they select stars based on how close they are. This removes a powerful bias. It allows astronomers to see what is actually common rather than what is merely conspicuous. Within a few parsecs, the results are clear. The typical star is small, cool, and faint. The Sun itself is brighter than most of its neighbours. This has profound implications for understanding stellar evolution, planet formation, and the potential for habitable worlds. Nearby stars are prime targets for searching for planets, precisely because their distances are known so well. A planet orbiting a star a few parsecs away produces clearer signals than one orbiting a star hundreds of parsecs distant. Again, the parsec underpins this clarity. When astronomers search for exoplanets using techniques like radial velocity or astrometry, distance matters. The closer the star, the larger the effect of an orbiting planet appears. Stars only a few parsecs away are ideal laboratories for these studies. This practical advantage reinforces the parsec's role as a working unit. It is not just about mapping space, it is about enabling precise measurement. There is also a dynamical aspect to nearby stars that becomes accessible at these distances. Proper motion, the slow drift of stars across the sky due to their actual movement through space, becomes measurable. Over years and decades, stars a few parsecs away noticeably change position relative to distant background stars. This motion tells a story about the structure and dynamics of the galaxy. It reveals that stars are not fixed points, but travellers, each following its own orbit around the galactic centre. By studying proper motions and distances together, astronomers can reconstruct three-dimensional velocities. Once again, parsecs provide the spatial framework that makes this reconstruction possible. Stars a few parsecs away also allow astronomers to study stellar multiplicity. Many stars are not solitary like the Sun. They exist in binary or multiple systems. Nearby systems can be resolved into individual components. Their orbits can be tracked. Their masses can be measured directly. These measurements anchor theoretical models of how stars form and evolve. They test predictions. They expose surprises. All of this depends on knowing distance accurately. It is worth pausing to consider how small this region really is in galactic terms. A few parsecs is a tiny fraction of the Milky Way's diameter. The galaxy spans tens of thousands of parsecs. The solar neighbourhood is a minuscule bubble carved out of an enormous disk. And yet, this bubble is disproportionately important. It is the region where measurement is easiest and most reliable. It is where abstract concepts can be checked against detailed observation. It is where the parsec feels least abstract, not because it becomes intuitive, but because it becomes useful in concrete ways. This usefulness changes how astronomers think about closeness. Closeness in astronomy is not about reachability, it is about resolution. A star a few parsecs away is close because it can be studied in detail, not because it can be visited. This redefinition of closeness is subtle but essential. When you hear that a star is only a few parsecs away, it does not mean it is within any practical sense of approach. It means that its distance is small enough, by cosmic standards, that our measurements are sharp and our inferences reliable. This reframing helps reconcile the word only with the vastness it hides. There is also a temporal dimension, even though the parsec itself is not a unit of time. Stars a few parsecs away are observed as they were a few years ago because that is how long their light takes to reach us. This delay is small enough that it rarely matters for stellar evolution, which unfolds over millions or billions of years. In this nearby region, the universe feels almost current. That sense of immediacy is another reason these stars are so valuable. They offer a view of stellar physics that is not significantly blurred by deep time. They show stars as they are now, within the limits of human timescales. This makes them reference points not just in space, but in understanding. The parsec quietly encodes all of this. It defines the scale at which the galaxy transitions from abstract population to individual objects. Beyond a few parsecs, stars begin to blend together in statistical studies. Within a few parsecs, each star can be known. This threshold is not sharp, it is gradual. But the parsec provides a way to talk about it with precision. When astronomers compile catalogues of nearby stars, they often choose cutoffs like 10 parsecs or 25 parsecs. These numbers are not chosen for aesthetic reasons. They reflect the reach of reliable measurement and the desire for completeness. Within these volumes, astronomers can be confident that they have found nearly all stars above a certain brightness or mass. Completeness matters. Without it, conclusions about stellar populations become skewed. The parsec helps define volumes where completeness is achievable. From a human perspective, this all happens far beyond sensation. You cannot look up and point to a star and feel that it is 3 parsecs away, rather than 5. The sky does not announce this information. It must be inferred, but once inferred, it becomes foundational. Stars only a few parsecs away are not special because they are dramatic or beautiful. They are special because they are close enough a distance to stop being the dominant uncertainty. They allow other uncertainties to come into focus. In this way, the parsec shapes not just measurement, but attention. It tells astronomers where to look if they want clarity rather than scale. It becomes clear that the parsec's role is not to make distance feel smaller. It is to make knowledge more precise. Within a few parsecs, the universe becomes less about guessing and more about measuring. That shift, from guessing to measuring, is where science does its quiet work. Once distance moves beyond the scale of individual stars, something subtle but decisive happens to understanding. Even the thin thread of familiarity that nearby stars provide begins to dissolve. Galaxies do not sit at distances that invite comparison, analogy, or bodily reference. They exist in a regime where intuition does not merely struggle but quietly withdraws altogether. Numbers still exist, units still apply, measurements remain precise. But the mind no longer tries to picture what those measurements mean in lived terms. This is where galaxies live, in distances beyond intuition. Within a few parsecs, distance still carries some practical meaning. Stars can be catalogued individually. Their motions can be tracked. Their environments can be studied. Once you move outward to hundreds, thousands, and millions of parsecs, the nature of distance changes. It stops being about separation between objects you might imagine approaching and becomes a statement about structure, arrangement, and scale. Galaxies are not just far away. They are far away in a way that breaks the habit of thinking in steps, journeys, or travel times. When astronomers describe the distance to another galaxy, they almost never do so with the expectation that anyone will try to imagine crossing that space. The distance is not a challenge, it is a context. It tells you where that galaxy sits in relation to others, how its light has been stretched by expansion, how its gravity interacts with its surroundings. The parsec becomes indispensable here because it scales cleanly into this regime. Distances to nearby galaxies are measured in hundreds of thousands of parsecs, or hundreds of kiloparsecs. Larger separations are measured in megaparsecs. At these scales, the parsec stops feeling like an odd unit and starts feeling inevitable. There is simply no other way to talk about these separations without drowning in zeros or losing all connection to observation. The Milky Way itself spans tens of thousands of parsecs. From edge to edge, it stretches across a disk whose dimensions only make sense when expressed this way. Saying the galaxy is about 30,000 parsecs across does not make it feel small or large. It makes it measurable. Once you step outside the Milky Way, parsecs multiply rapidly. The nearest large galaxies lie hundreds of kiloparsecs away. Galaxy groups span megaparsecs. Clusters of galaxies stretch across tens of megaparsecs. The large-scale structure of the universe, the cosmic web itself, is mapped in hundreds of megaparsecs. At this point, intuition has no foothold at all. There is no human experience that corresponds to these distances. There is no analogy that does not collapse under its own cleverness. Even light years, which once felt helpful, become unwieldy here. Saying a galaxy cluster spans tens of millions of light years does not feel meaningfully different from saying it spans hundreds of millions. The numbers blur. Parsecs do not rescue intuition, they replace it. This replacement is not meant to comfort, it is meant to allow work to continue. When astronomers study galaxies, they are rarely concerned with individual stars. They care about populations, distributions, and dynamics. They care about how mass is arranged, how galaxies interact, how clusters form and evolve. For these questions, distance is a parameter in equations, not a sensation to be imagined. Parsecs integrate naturally into these equations. For example, when astronomers measure the brightness of a galaxy and combine it with its distance in megaparsecs, they can infer its total luminosity. That luminosity in turn informs models of star formation, chemical enrichment, and energy output. The distance does not need to be felt. It needs to be correct. Similarly, when mapping galaxy clusters, astronomers care about separations between galaxies in 3 dimensions. They want to know how far apart they are, how fast they are moving relative to one another, and how their gravitational fields overlap. Expressing these separations in megaparsecs allows these relationships to be described cleanly and consistently. At this scale, distance stops being a single number and becomes part of a pattern. Galaxies are not sprinkled randomly through space. They cluster. They form filaments. They surround vast voids. These structures are defined by distances measured in parsecs on a scale that dwarfs anything human intuition can manage. The cosmic web is not something you imagine walking through. It is something you map statistically. This statistical nature is another reason parsecs dominate galactic astronomy. They align naturally with volume calculations. Densities are expressed per cubic megaparsec. Correlation lengths are measured in megaparsecs. Expansion rates are defined per megaparsec. These are not arbitrary choices. They reflect how the universe organizes itself on large scales. At galactic distances, even the idea of closeness changes again. 2 galaxies separated by a few hundred kiloparsecs may be considered neighbors, part of the same group. 2 clusters separated by tens of megaparsecs may still influence each other, gravitationally over cosmic time. Closeness here is not about proximity in a human sense. It is about interaction. Distance beyond intuition becomes a functional concept rather than an experiential one. Another shift occurs when distance is tied to cosmic expansion. At very large scales, galaxies are not simply sitting at fixed separations. The space between them is stretching. Distances measured in megaparsecs change over time as the universe expands. This expansion is not something you feel. It does not tug on your body or stretch your surroundings. It is detected through the redshift of light and described through models that depend on distance scales expressed in megaparsecs. Here again, parsecs prove their worth. Key cosmological parameters are defined using megaparsecs. The expansion rate of the universe is expressed as a velocity per unit distance, typically kilometers per second per megaparsec. This formulation would be awkward or meaningless in other units. The parsec becomes woven into the fabric of cosmological language. This weaving reinforces the idea that distance at these scales is not about separation alone. It is about relationship. Relationship between galaxies, between mass and motion, between geometry and time. Trying to feel these distances is not just difficult, it is unnecessary. The mind often rebels against this. It wants to visualize. It wants to imagine flying past galaxies, counting the years, watching the stars drift by. These images are compelling, but they are distractions at this scale. They suggest continuity where there is none, narrative where there is structure. Galactic distances are not stories, they are coordinates. When astronomers say a galaxy lies 10 megaparsecs away, they are not inviting you to imagine 10 million parsecs stacked end to end. They are telling you where that galaxy sits in the cosmic arrangement. They are giving you a location, not a journey. This distinction matters because it reframes what distance is for. Distance beyond intuition is not meant to be internalized. It is meant to be referenced. Just as you do not need to imagine the entire Earth every time you use latitude and longitude, astronomers do not need to imagine the full span of megaparsecs every time they use the unit. The number serves as a coordinate in a larger system. This coordinate system allows astronomers to compare observations across vast scales. A galaxy at 5 megaparsecs can be meaningfully compared to one at 50 megaparsecs, not because the difference feels 10 times larger, but because the underlying physics scales accordingly. Light diminishes with distance. Expansion affects redshift. Gravitational influence weakens. These relationships are captured mathematically, not emotionally. The parsec enables this capture. There is also a kind of intellectual calm that comes with accepting distance beyond intuition. Once you stop trying to force meaning into feeling, the numbers become less oppressive. They stop demanding imagination and start offering structure. Galaxies measured in parsecs become points in a map, rather than destinations in a story. This does not make them less wondrous. If anything, it makes their arrangement more astonishing. The fact that structures spanning millions of parsecs exist at all, that matter organizes itself on such scales, is remarkable. But the wonder arises from pattern, not from imagined travel. Understanding this helps reconcile the emotional gap many people feel when confronted with cosmic distances. The discomfort is not a failure of comprehension. It is a signal that you are trying to use the wrong mental tool. Human intuition evolved for meters and kilometers, not megaparsecs. Expecting it to function unchanged at galactic scales is unreasonable. Astronomy adapts by changing the tool. The parsec, scaled up into kiloparsecs and megaparsecs, becomes the language that replaces intuition when intuition can no longer contribute. It allows astronomers to continue asking meaningful questions even when imagination has stepped aside. Those questions are not about how far you could go. They are about how things are arranged, how they move, and how they change over time. Galaxies measured in distances beyond intuition are not meant to be felt. They are meant to be understood structurally. This understanding deepens with time, not because the distances become familiar, but because the relationships become clearer. Patterns emerge, distributions make sense, models converge. The parsec remains at the center of this process, quietly anchoring the map. As this perspective settles, it becomes easier to let go of the need to imagine galactic distances in human terms. You do not need to feel them to appreciate their role. You only need to accept that at some scales, meaning comes not from sensation, but from structure. In that acceptance, the universe opens up not as a place to be crossed, but as a system to be understood. There is a quiet assumption that sits beneath many questions about science, one that rarely gets spoken aloud. It is the assumption that measurements should feel natural, that units should align with intuition, that numbers should cooperate with the way the human mind prefers to organize the world. When they do not, the discomfort is often framed as a flaw in explanation, or an unnecessary complication introduced by experts. The universe does not share this assumption. Again and again, when humans push their measurements beyond familiar territory, the numbers begin to behave strangely. Units become abstract. definitions grow indirect. Concepts rely on relationships rather than objects. This is not because scientists enjoy obscurity. It is because the universe does not scale smoothly from human experience outward. It changes character, and measurement has to change with it. The preference for strange measurements is not aesthetic. It is structural. On Earth, measurements evolved to solve local problems. Lengths were defined by bodies, tools, and landscapes. Time was defined by cycles of light and darkness, seasons and years. Mass was defined by what could be lifted, traded, or stored. These units worked because the environment they described matched the scale of the organism doing the measuring. Once you leave that environment, the match dissolves. The universe beyond Earth does not organize itself around bodies, journeys, or effort. It organizes itself around motion, interaction, probability, and geometry. When humans insist on carrying familiar units into that environment, the units begin to strain. They still work mathematically, but they no longer describe reality in a way that aligns with how that reality is encountered. This is the moment when measurements start to feel strange. The Parsec is one example, but it is far from the only one. Astronomy is filled with units that feel indirect, relational, or even evasive to human intuition. Luminosity rather than brightness, redshift rather than velocity, magnitude scales that run backward, distances defined by angles instead of lengths, time measured in half-lives rather than minutes. These choices are not arbitrary. They reflect the constraints imposed by observation. The universe does not present itself as a set of objects waiting to be measured directly. It presents itself as signals, light arriving from far away, particles interacting briefly, motions inferred from shifts and delays, patterns emerging from statistics. When what you observe is indirect, your measurements must be indirect as well. This is where the idea of preference becomes misleading. The universe does not prefer strange measurements in the sense of having taste or intention. It enforces them. It leaves no alternative if you want accuracy. Consider distance again. On Earth, you can measure distance by traversing it, by laying down a ruler, by sending a signal and timing its return. In space, especially at large scales, none of these options are available in a direct sense. You cannot travel the distance. You cannot lay down a ruler. You cannot bounce a signal off a star and wait for it to come back. What you can do is observe how things appear to change when your position changes. Distance becomes something you infer from geometry, from angles, from relative motion. The unit that describes that distance must reflect the method, not the desire for familiarity. The Parsec does exactly that. This pattern repeats across science. Temperature, at human scale, feels like warmth or cold. At atomic scale, temperature becomes a measure of average kinetic energy. The sensation disappears. The unit remains, but its meaning shifts. Time at human scale feels like flow. At relativistic scale, time becomes dependent on motion and gravity. It stretches and compresses. The unit remains, but its behavior changes. Mass at human scale feels like heaviness. At subatomic scale, mass becomes interchangeable with energy. Particles appear and disappear. The unit remains, but intuition breaks. Each time this happens, there is resistance. People ask why the measurement has to be so strange, why it cannot be simpler, why it cannot be expressed in terms that feel natural. The answer is always the same. Because natural to humans is not natural to the universe. The universe does not experience itself. It does not need measurements. Measurements exist for observers, and observers are constrained by what they can detect. When detection is indirect, measurement becomes indirect. This is particularly evident in astronomy, because the observer is so thoroughly separated from the objects being observed. The distances are vast. The timescales are immense. The signals are faint. Nothing can be touched. Nothing can be manipulated directly. Astronomy is the science of inference. In an inferential science, Units that encode method are more valuable than units that encode sensation. A strange measurement is often a more honest one. The parsec, again, is instructive here. It feels strange because it does not describe what distance feels like. It describes how distance is known. It embeds the observing process into the unit itself. This embedding is common in astronomical measurements. Magnitudes encode ratios of brightness rather than absolute values. Redshift encodes relative stretching of light rather than velocity directly. Distances encode geometry rather than length. These choices reduce error. They keep the measurement close to the data. Familiar units often require additional assumptions. To convert brightness into luminosity, you need distance. To convert redshift into velocity, you need a cosmological model. To convert angular size into physical size, you need geometry. When a unit avoids unnecessary conversion, it avoids unnecessary assumption. Strangeness in this sense is efficiency. There is also a deeper reason why the universe resists human-friendly measurement, one that has less to do with observation and more to do with structure. The universe is not uniform across scales. The rules that govern behaviour change as you move outward or inward. At small scales, quantum effects dominate. At intermediate scales, classical mechanics works well. At large scales, relativity becomes important. At the larger scales, expansion shapes everything. Each regime demands different tools. Trying to use the same measurements across all regimes creates confusion, not clarity. A unit that works beautifully at one scale may be misleading at another. The universe forces specialization. This specialization feels strange only if you expect continuity where none exists. Human intuition expects smooth scaling. A longer distance should feel like more of the same. A longer time should feel like extended waiting. The universe does not scale that way. It shifts regimes. When the regime shifts, measurement must shift too. This is why strange measurements proliferate as science advances. Each new domain exposes the limits of previous tools. Each new scale demands new language. Resistance to this process often takes the form of nostalgia. People want the universe to remain describable in terms that feel comfortable. They want to hold on to familiar numbers as anchors. But anchors only help if the ground beneath them holds. In deep space, the ground does not hold. The parsec, the light year, the astronomical unit, the megaparsec all exist because earlier anchors failed. Each one emerged not to confuse, but to restore coherence at a new scale. The fact that coherence comes at the cost of intuition is unfortunate, but unavoidable. There is also a cultural element to this discomfort. Modern societies place high value on accessibility. Concepts that cannot be easily explained are often viewed with suspicion. Complexity is associated with obfuscation. Simplicity is associated with honesty. In science, this association is unreliable. Sometimes the simplest description is the least accurate. Sometimes a strange unit is the clearest one available. The universe does not adjust itself to pedagogical preferences. This does not mean explanation is pointless. It means explanation has limits. No amount of metaphor can make a parsec feel like a walk. No analogy can make a megaparsec feel like a journey. At some point, explanation must shift from sensation to structure. When that shift is resisted, misunderstanding follows. People accuse science of being detached, abstract, or elitist. In reality, science is responding to a reality that does not cooperate with everyday thinking. The universe prefers strange measurements because it is strange, not in a mystical sense, in a structural sense. Its scales, motions, and relationships differ radically from those that shaped human perception. Measurements that reflect those differences will necessarily feel alien. There is a quiet humility required to accept this. It requires acknowledging that human intuition is not a universal tool. It is a local adaptation, effective within a narrow range, useless beyond it. Science progresses by recognizing this limitation and working around it. Strange measurements are not a failure to explain. They are a sign that explanation has moved beyond the body. There is also a calming aspect to this realization once the resistance fades. You're not expected to internalize every scale. You're not required to feel every distance. You're allowed to let the universe be larger, older, and more complex than your instincts can handle. The numbers can exist without you. This is often framed as alienation, but it can also be framed as relief. The burden of comprehension is shared between intuition and abstraction. When intuition reaches its limit, abstraction takes over. The Parsec lives entirely in that abstract space. It does not ask you to imagine it. It asks you to use it. It does not care whether it feels strange. It exists because it works. The universe does not care about comfort. It cares about consistency. When astronomers adopt strange measurements, they are not bending reality to their will. They are bending language to fit reality as closely as possible. The resulting language feels unfamiliar because reality at that scale is unfamiliar. This unfamiliarity does not diminish wonder. It deepens it. There is something profoundly humbling about realizing that the universe cannot be fully translated into human terms, that some aspects of it resist domestication, that some distances will never feel like anything. In that resistance lies a quiet reminder. The universe is not an extension of human experience. Human experience is a tiny pocket within the universe. Strange measurements are the cost of exploring beyond that pocket. Once you accept that cost, the strangeness loses its edge. It becomes simply another feature of a reality that does not owe us familiarity. The universe does not prefer strange measurements because it wants to confuse. It enforces them because accuracy demands it. And accuracy, unlike intuition, scales with reality rather than comfort. As this understanding settles, the Parsec and its companions stop feeling like obstacles. They become signposts, marking the point where human-scale thinking gives way to something larger, quieter, and more exact. There is a moment that comes after the numbers have piled up, after the definitions have been unpacked, after angles, baselines, and distances beyond intuition have all had their turn. It is not a conclusion exactly. Nothing is being wrapped up. Nothing is finished. It is more like a settling. The way your body settles into a chair after you stop adjusting your position. The way your breathing settles once you realize there is nothing else you need to do right now. This is where the idea of a very, very large universe finally has room to rest. Not to be understood in full, not to be imagined clearly, just to be acknowledged without resistance. For most of the journey so far, the focus has been on how humans measure what they cannot reach, on why certain units feel strange, on how distance becomes abstract when it grows beyond experience. All of that work is necessary, because without it, the universe feels either misleadingly small or impossibly confusing. But once the work is done, there is a quieter realization waiting underneath. The universe does not become smaller when you understand it better. It becomes calmer. This calm does not come from mastery. It comes from acceptance. A parsec does not suddenly feel familiar. A megaparsec does not become imaginable. Galaxies measured in millions of parsecs do not suddenly line up neatly in the mind. Instead, the pressure to force them into human scale eases. The mind stops demanding that distance behave like distance always has before. The universe remains large. It remains very large. But it no longer needs to be argued with. There is something psychologically exhausting about trying to compress cosmic scale into human terms. Every analogy strains. Every metaphor breaks. Every attempt to feel the size of things ends in frustration or false comfort. At some point, the effort itself becomes the problem. Settling back means letting that effort go. It means allowing the universe to be large without insisting that largeness be translated into sensation. It means recognizing that knowledge does not always arrive with intuition attached. Sometimes it arrives as structure, as relationship, as quiet consistency. The parsec is part of that consistency. Earlier it may have felt like an obstacle. a unit with a name that felt wrong, a definition that resisted storytelling. But now, after tracing where it comes from and how it is used, it begins to feel less like a barrier and more like a railing, something you can lean on without having to look down the entire distance. This shift is subtle, but important. The human mind is very good at oscillating between extremes when faced with vastness. Either it tries to dominate the scale, to reduce it, to make it manageable through analogy, or it recoils from it, declaring it incomprehensible and turning away. Neither response is particularly restful. Settling back is neither domination nor retreat. It is the recognition that you do not have to carry the scale of the universe inside you in order to coexist with it. You do not need to feel every distance. You do not need to imagine every gap. You only need to accept that the gaps exist, measured carefully, consistently, and patiently by people who have learned to work within that vastness rather than against it. The phrase, very, very large, is doing something deliberate here. It is intentionally vague. It does not attempt to quantify. It does not compete with parsecs or megaparsecs. It acknowledges that beyond a certain point, adjectives replace numbers in human language not because numbers fail, but because numbers stop needing reinforcement. The universe is large enough that repeating the fact adds nothing, and yet repetition is comforting. There is comfort in returning to the idea without pressure, in letting the size of things sit in the background rather than dominate attention, much like the night sky itself, which can be overwhelming if stared at too intently, but soothing when allowed to exist at the edge of awareness. This is where distance stops being confrontational. Earlier, distance demanded explanation. It demanded justification. It demanded new units and strange measurements. Now, distance simply is. It stretches. It separates. It structures. It does not ask for reaction. The universe does not lean closer when you understand parsecs. It does not become more intimate. What changes is your posture toward it. You stop trying to close the gap. This is not resignation. It is realism. The gap between human scale and cosmic scale is not a flaw to be corrected. It is a feature of existence. The universe did not evolve around human perception. Human perception evolved within a very narrow pocket of the universe. Expecting that pocket to generalize outward indefinitely is unreasonable. Once that expectation dissolves, the relationship becomes easier. Consider how often discomfort arises not from size itself, but from the mismatch between expectation and reality. When you expect something to be manageable and it is not, frustration follows. When you expect something to be familiar and it is not, confusion follows. But when you expect something to be large, distant, and indifferent, and it turns out to be exactly that, the emotional response softens. The universe keeps its promises. It is large. It is distant. It is structured in ways that do not center you. Knowing this removes the tension of surprise. The parsec, once misunderstood, becomes a quiet reassurance of that structure. It tells you that distance is not arbitrary chaos. It is mapped. It is measured. It is handled with care even if it cannot be felt. There is something grounding about that. People sometimes worry that abstraction drains meaning from the universe, that turning stars into numbers and distances into units strips away wonder. In practice, the opposite often happens. Wonder becomes less frantic, less performative. It becomes steadier. You no longer need the universe to impress you with scale. It already has. You no longer need to imagine travelling across it. You already know you cannot. This frees attention for something subtler. For example, the fact that despite its size, the universe obeys patterns, that galaxies cluster rather than scatter randomly, that stars form according to consistent rules, that distances, however large, fit into coherent frameworks that allow prediction and understanding. Large does not mean chaotic. The parsec exists because order exists at scales far beyond human experience. It exists because geometry still applies, because angles still behave, because motion still reveals structure. If the universe were truly incomprehensible, no unit would help. The parsec would be meaningless. Its usefulness is evidence of intelligibility. This is an important point to let settle. The universe is not just large. It is knowable in parts, not through sensation, but through careful observation and patient reasoning. That knowledge does not collapse the universe into something small. It allows humans to orient themselves without pretending centrality. Orientation is different from ownership. Settling back means allowing yourself to be oriented without needing to be centered. This can feel unfamiliar, especially in cultures that emphasize agency, control, and narrative dominance. Space resists narrative dominance. It does not revolve around protagonists. It does not escalate toward conclusions. It does not respond to urgency. In that sense, it is deeply compatible with rest. There is no countdown embedded in cosmic distance, no deadline implied by a parsec, no pressure to arrive anywhere. Distances simply exist, spanning quietly between objects that themselves persist for millions or billions of years. Human anxiety struggles to attach itself to that timescale. When you think about a star a few parsecs away, or a galaxy millions of parsecs distant, there is nothing you are meant to do about that information. It does not require action. It does not demand response. It is not a problem to be solved. It is a condition to be acknowledged. This lack of demand is part of what makes settling possible. The universe does not need you to understand it tonight. It will still be there if you never do. It does not lean on your comprehension for its stability. That realization can feel small or large depending on how you frame it. But in moments like this, it tends to feel relieving. You're allowed to stop pushing. The parsec no longer needs defending. Light years no longer need comparison. Distances no longer need translation. They can recede into the background, doing their quiet work of organizing space while your attention drifts elsewhere. This is not forgetting. It is integration. The idea of a very, very large universe does not sit at the front of the mind all the time. It does not need to. It becomes part of the backdrop against which everyday concerns shrink slightly, not because they are unimportant, but because perspective widens. This widening does not make personal life insignificant. It makes it specific. Your location, your moment, your scale become clear. You exist at a particular distance from things that are very far away. That is neither good nor bad. It is simply true. Distance, once understood, stops being threatening. And as that understanding settles, there is room for quiet. Quiet is not emptiness. It is the absence of pressure to resolve. The universe remains very, very large. Parsecs continue to stack into kiloparsecs, megaparsecs, beyond anything human language can comfortably hold. Galaxies continue to drift. Light continues to travel. Earth continues its orbit, serving quietly as a measuring tool whether anyone is paying attention or not. Nothing here depends on urgency. You do not need to reach the edge of understanding. There is no edge to reach. You do not need to imagine the full scale. You cannot. That is not a failure. Settling back means allowing that impossibility to exist without irritation. Just as you allow the horizon to remain distant without trying to walk to it every time you see it. The universe does not need to be brought closer to be meaningful. It can remain vast and still be part of your mental landscape, like the sky itself, always present, rarely demanding. As this settles, attention can soften, thoughts can slow, the numbers can fade without being rejected. The structure remains even when focus drifts. The universe is large enough to hold both precision and rest, and in that largeness, there is no rush, no requirement to conclude, no signal that anything needs to end. There is only the continued presence of distance, measured carefully, existing quietly, stretching on well beyond intuition, whether you're thinking about it or not.